another 10 more years to
Oh,
go.
yeah, this is very, very, very young then. I think
Yeah.
because I'm sure I heard the name, but I don't remember when I heard it. Okay, okay. That
One
means
of the classes. Yeah.
you probably joined LLN probably around 1980.
No, when I joined TNB in
Oh, yeah,
97,
TNT. Oh, that means you joined very late. Okay, okay.
97. Yeah.
That was after I left LLN already. Okay. Kennedy, so in case you got any contributions, don't feel shy about contributing. Maybe that's without getting you into trouble with your bosses. So any experience you want to share, of course, will be most welcome.
All right. Thanks a lot.
Okay.
Really.
Okay. Waiting for. How many people have we got? Win. Win. How many people have we got? Win is not on the line yet. No. Oh, no, Shamir. No, Shamir. Ayah, you just wrote in yesterday. You're from not Intel. Ayah. Where are you from? No, Shamir. Now I just can't remember. No, cannot remember already. Jeffrey Teo from Kuching, PKM Kuching. Okay. Let me get ready first. So I'm going to start in a little while. Just to give you some ideas, what's going to happen is that next month, of course, I'm supposed to have one on current transformers, the next webinar. So hopefully we get a good crowd, because current transformers, I'm going to try to deal with it in a way that makes more sense, because otherwise current transformers is one of those things we don't really pay attention to. So let's make I'll try to make more sense. And in between, I was thinking of doing a short circuit protection. This is requested by somebody in Petronas, but looks like I don't have enough time. Too many assignments going on. So I probably, and then the next month, April, of course, is Ramadan. So I don't like to do courses during Ramadan. So probably we'll start again in May. Okay. So Win, are you online, Win?
Yep.
Okay. How many people have we got now, Win?
Sorry?
How many people have we got now?
Let me quickly check. 76.
Oh, 76. Oh, still some way to go. The reason is because we have more than 130 people. I think probably 134 if I remember by now. Okay, so 76 is a bit low. So, okay, never mind. I will start by telling you something else. I won't go into the cost material yet. Now, the problem...
Engineer Lee, you want me to start recording?
Yeah, you can.
Okay.
Thank you. Okay. Good morning. Selamat pagi to all of you. So we are expecting a crowd of 130 people, 134. We got people from all over the world. The furthest is probably there's a guy from New Zealand, but he just called up to say he can't make it. There's a Adash who's from India, based in Korea. We have a few people from Singapore. Three different companies from Singapore. Then we have a big contingent from Brunei, Barakas Power, very much involved in generation, distribution, and projects in Brunei. The biggest group is from Renhill. We got 12, in fact 13 people. So thanks very much for your support. And from GSO, GSO is a grid system operator which runs the NLDC. And of course, NLDC is the one that controls our transmission system. So we have 3 people. So all in all, we have 100 people. So, okay, so let me start by telling you that this is going to be a very challenging course. But before we even get there, I'm going to tell you what it doesn't include. Although the title says transmission, it doesn't include 1.5 breakers. What is 1.5 breakers? That's a type of switchgear arrangement that is used at the highest voltage level at 275 kV, as a 500 kV in Malaysia. Sarawak, I'm not very sure. Okay. But in Brunei, they use it as low as 66 and 132. It's the highest standard that we have for switchgears, 1.5 breakers. Sounds very strange. Okay, so we won't cover that because there are very few of these substations even in Semenanjung. Okay. The other thing that we will not cover is transformers. Why? Because transformers have been covered earlier under a topic by itself. So what are we going to talk about today? Because I'll come back to that later on. But I want to start by telling you that talking about transmission protection is a very challenging assignment. Why? Because most of you are very familiar with dealing with, okay, I'm going to divide electricity into 4 areas. We have generation, we have transmission, distribution, and we have utilization. Now, generation, of course, is a totally different field. Can stand alone by itself. But between distribution and utilization, that is the industries, the commercial or consumers, they are more or less similar. They use basically up to medium voltage. But transmission is a totally different thing. And the standards that we are going to apply in transmission is very, very much higher. And that makes our life very difficult. So what's the challenge in transmission engineering, protection engineering? The biggest challenge is this. We are going to use different type of relays, and we're going to treat them differently. Now, in distribution, in utilization, in our plants and so on, what do? We have the usual overcurrent of our relays, we have transformer protection, we have differential protection, we have protection for our cables. Nowadays, everybody uses current differential relays. So we have main protection, the first relay to operate, and we have a backup protection. What happens if something goes wrong? And then for that we use overcurrent. And in general, the bus bars do not have a dedicated protection. The bus bars are protected by the overcurrent fault relays, which is, of course, very slow. But that's the accepted norm, at least in Malaysia. Other countries, for example, in Dubai, even the 11 kV, they also put in a bus bar protection. But that's not the standard that we have here. Now, what's the difference between that and in transmission? Transmission, we are talking about totally different level of protection. In transmission, we're going to say, hey, anything that has to be protected must be protected by a differential relay. Not like distribution, 11 kV bus bar, 33 kV bus bar. The overcurrent fault relay for the incomer is the main protection, and that's very slow. But in transmission, every piece of equipment must be protected by a unit protection, a differential protection, and that will clear the fault within 100 milliseconds. Now, what happens in the main protection field? In distribution, we rely upon overcurrent of fault relays. In transmission, we cannot use overcurrent of fault relays. Why? Because the distribution in general consists basically of a radial network, maybe with some generation at that end, but very little, not complicated. But in transmission, we are talking about interconnected systems with connections between power stations, big power stations, and now, of course, we have all these solar plants, renewable energy plants. All these are called interconnections, and all these interconnections will feed power into the network, and they feed fault current. So how do we operate them? We operate them as an integrated network. We operate them as parallel networks. In distribution, we also operate them as parallel network, but maybe with 2 cables. That's it. But in transmission, you could have a substation with sources coming in from 2 or 3 different power stations, okay, or with interconnections with solar plants. So is it good? Of course, it's good because you got more power supply, you got better reliability, but it also complicates our thing. What happens if there's a fault? Remember, in transmission, we have this very fast differential protection that will trip. And if every time there's a fault, transmit the main protection, which is the first protection to operate, we use a differential relay. The main protection will trip very quickly, and that's the end of the story. The complication starts is when that main protection fails. Very unlikely, but it can. And in distribution, what do? If a differential relay fails, we say, we have an overcurrent of our relay. But in transmission, we do not do that. Why? In distribution, it's very easy. You got basically one flow of current, a radial flow. So if there's a fault, we know which direction the current coming from. Maybe because of generation, maybe with some PV plant, but at the most, some current, maybe some current could going the other way, but most of the time we don't worry too much. But in transmission, if there's a fault, current can come from multiple sources, and it's impossible to grade them. In other words, sometimes the fault is in a place, you want this relay to be fast, the other relay to be slow. But if the fault next time changes to the other end, you want the other relay to be fast and the first relay to be slow. So you cannot grade them. You can try to use direction of a current relays, but they still don't work very well. So in transmission, we do not use overcurrent of fault relays. We use distance relays. And distance relays have one problem. There are limitations to the settings, which you will see. So that's one of the biggest challenges. That you find that unlike the overcurrent of fault relay, distribution relay don't provide, distance relays don't provide very good backup protection. In reality, it doesn't. Okay, so what can go wrong with the transmission system or in any system with regards to protection? If there's a fault, we expect the main relay to operate, and the main relay doesn't operate, we have a backup relay that will operate, overcurrent of fault relay, for example. Next complication is what happens if you have two parallel feeders feeding a distribution system. You have two incoming transformers feeding, say, a bus bar. So what happens is a fault? Is it good or not to have two transformers feeding a bus bar? Very good, because you have better reliability. But in the distribution system, what happens is a fault and the main protection fails. Every time the main protection operates, we have no problem. But if the main protection fails, for example, for a bus bar fault, what happens now? Now we have two transformers feeding into the fault. And the backup relays are on the two incomers for the transformers. So if there's a fault, for any reason, the main protection fails. Now we have two backup protection that will trip because we have two feeders. And we accept that for distribution. Sorry, we have a fault, the main protection failed, we lost both incomers. We accept it. But do we accept that same philosophy for transmission? No, we are not going to accept that. So what can go wrong in general with the protection system? So I'm going to tell you there are three things. The worst is if you have a DC failure. That you have a DC failure, and if you don't attend to it quickly, it's a time bomb waiting to explode. And I hope it doesn't happen. It has happened many times. I hope it doesn't ever happen again. The next thing that can go wrong is the relay can fail for various reasons. So I won't go into it. But the next thing that can fail is a circuit breaker can fail. So there have been cases circuit breakers fail. So what happens if any of this happen in the distribution system? We have the backup. And if the backup relay trips two incomers, we lost the supply. Because of single failure, we accept it. But that's not acceptable in transmission because of higher standards of reliability. So we cannot say, oh, there was a failure of a relay. I have two incomers. So what happened? What to do? One relay failed, two relays operate as backup. That is not acceptable. Or the breaker itself failed. Have breakers failed? Yes, they do fail.
Sorry,
you cannot say, well, one relay failed, one breaker failed. Sorry, is there a question? One relay failed, one breaker failed. Cause loss of supply, total loss of supply to the substation. We cannot accept that. So to prevent that, we need to have extra protection in transmission, which we don't do in distribution. The other complication is in transmission.
Sorry,
Epicenter.
can you show? Are you sharing any slide?
No, not yet. I'm just talking in general only.
Okay.
Oh,
Just
I
talking in
see.
general. Okay, sorry. So I'll go to the slide a bit later. So I'm just giving you my philosophy first. So what happens if you have a busbar fault? In transmission, we need a busbar protection, which we don't have in distribution in general. And the busbar protection can be a bit complicated. So what I'm going to cover today, okay, now we are going to cover this, for this webinar, we're going to cover this. We're going to talk about protection philosophy. Actually, I've changed the notes quite a bit, but never mind, I'll stick with this flyer. We're going to talk about protection philosophy. We're going to talk about the significance of the location of protection cities. So here I'm looking at the flyer that I sent out to you all. Then we'll look at differential protection for cables and lines. And then we're going to look at, distance protection. Here, we'll look at distribution protection, distance protection. And then we're going to look about busbar protection. That's what we're going to cover today. When I first started with this, I had probably about 140 slides. But by the time I finished, and I thought 140 is a nice number to do my 8-hour webinar. Why? I probably take about 70 to, I can do about 70 to 80 slides in 4 hours. But by the time I finished, I had about 190 slides. So which means I'm going to run into a time problem. So I'm going to tell you that certain slides are there for information, or in case anybody asks questions, I will not cover all the slides. Okay, I'll just say, okay, this is there. In case nobody asks question, I'm going to skip it. So there are some slides for extra information. Now, the last protection topic we're going to talk about today is busbar protection. And at the end of it, I'm going to do a test, a quiz. But from my previous experience, I look at the results of the quizzes I've carried out, and I find that a lot of times what I said, the participants have not understood it. So I get a bit agitated. So what can I do? So since it's a very difficult topic, and to make sure that you understand what I'm asking you, so I will change the tactic a little bit. So what I'll do is at every section, at the end of every section, I will do a test. Okay, but this test is open test in the sense that we just you don't answer, we will just, I'll show you the question and somebody will just give the answer and we'll discuss the answers. Okay, and then we'll go into the quiz. Hopefully I have enough time. We'll go to the quiz at the end of today's session, and to make sure that you do well in the quiz, because it's in my interest to make sure you do well. It's my interest to make sure you understand. Just before the quiz, I will repeat some of the points, giving you the tips. What are the answers? More or less telling you what the answers are. Then we will do the test. So hopefully that improves the level of understanding. And so what we are talking about today are basically the basic protection that we have talked about. But now we're going to introduce one more topic called busbar protection. Okay. For next week, I'm going to talk about the extra protection that we don't have at distribution. The bonus protection. What happens if a relay fails? What happens if a breaker fails? So in transmission, you find that we have two extra protection called backup protection. Called breaker failure and bus separation. The other complication here is, whatever I say here, you may say, hey, we don't do it. For example, maybe we don't do it in Sarawak, or we don't do it in Singapore or New Zealand. Yes, every utility have their own protection philosophy. So I'm just sharing to you what I know based upon the philosophy in Malaysia. So the philosophy in Malaysia is what I know is based upon what is practiced by our local utility. For those of you who are from outside Malaysia, our local utility is called TNB, National Energy, Tenaga Nasional, TNB. So very often I refer to TNB, I'm referring to our local utility, and you may find that somewhere else they have totally different ideas. Okay, so I obviously don't have the enough international exposure to share with you. I know quite a bit about Brunei, Oman, Oman and Malaysia are about the same, but of course I have Johnny here, Johnny Ling, who worked in Oman for a good many years. So in case any problem, I can refer to him. Okay, and the last topic that we will cover will be auto reclose. Okay, for transmission lines. And okay, let me see. I think the then after that, the next for next week we'll talk about testing of protection relays. So for today, we'll talk until up to the bus bars. Okay, so let me go through very quickly what we are going to, just to give a preview of what we're going to talk about. So protection philosophy is a term we use to describe what are the basic concept. So we call it protection philosophy for transmission system. So every piece of equipment, so I'm just reading to you what is written here. Every piece of equipment must be protected by at least one differential relay, okay, which will clear any internal faults within 100 milliseconds. How did they get 100 milliseconds? We'll see that, okay. And the equipment at the highest voltage. So the highest voltage, I'm going to call it EHV. Why? So I'm going to divide voltages into 4 volt levels. The low voltage, in this case, we're not going to talk about medium voltage. Medium, of course, 11 and 33 kV. Then, of course, we're going to talk about transmission. And transmission, I'm going to divide it, my own division, for up to 132, I'm going to call it HV. Above 132, I'm going to call it EHV. Why? Because what the protection philosophy for EHV is different from that of HV. I'll show that in a little while. So equipment at the highest voltage, anything more than equal or more than 275 kV, are protected by 2 differential relays. This is talking about TMB practice. So we have we have a transmission line. Instead of having 1 differential relay, we have 2 differential relays. We have a busbar protection. Instead of having 1 busbar protection relay, we have 2 busbar protection relay. Similarly, with the transformer, 2 differential protection. But the last one is not practiced by the consumer. So now the consumer will say, okay, the TMB line come in, I will put in giving 2 differential relay at 275 kV. The bus bars, I'll put in 2 differential relays. But for the transformers, I only put in 1. So there's a difference between what the consumers are doing and what TMB is doing. Okay. So every piece of equipment is protected, and at the EHV, we generally use 2 different differential relays. Why? In case one fails. Now, if you have 2 differential relays, how are you going to connect them? Because there are 2 different ways to connect them. So later in the notes, I use the word logic OR, logic AND. So the logic OR is what we use for transmission lines. That means you have 2 differential relays. If one trips, it will trip the line. We want to make sure a line fault will be clear. One of them trip is enough. The other one is in case the first one fails. But for bus bars, the philosophy is different. For bus bars, we don't want to trip the bus bar because 1 differential relay tripped wrongly. Or in other words, what happens if you have a line and you have 2 relays and 1 relay trips wrongly? Well, too bad lah. That's the price we pay. So we accept the fact that we have 2 relays, 1 can trip wrongly. And in the TMB system, if 1 relay trips wrongly for a line, it's not a big problem because they have enough spare capacity. 1 line trips, hopefully the other line still is in service. Even if it's not in service, probably there are other ways to supply this substation. So we accept that the price of this logic or condition is a possibility of loss of supply because the relay tripped wrongly. We accept that. But we don't accept that for busbar protection. We cannot say, we lost the whole of KLIA. Why? 1 busbar protection relay tripped wrongly. Sorry, too bad. No. So what we do? We have 2 relays, but we arrange them in different ways. We arrange them as a logic AND. That means both must trip at the same time before we can get the tripping. Then, of course, we end up with the opposite problem. What happens if 1 relay fails? Then we got no busbar protection. So to overcome that, at 275 kV, what do? We put in duplicate 2 out of 2 protection. So you can see the way things are going. So for 275 kV, not only we have 2 busbar protection relays, we have 4 busbar protection relays, all protecting the same equipment. So you can see the difference in the philosophy. Okay. But for transformers, as I said, consumers they don't do that. They only use one because transformers not likely to have transformer faults and transformer fault, if it fails, there are other ways. The relay fails, we can use the other methods to minimize the effect. So in general, the other difference between transmission and distribution is I told you earlier, we don't use overcurrent fault relays at transmission because of the difficulty of setting. It's impossible to set them. But starting from the transformer, starting from the HP side of the transformer, we start to use overcurrent fault relays. Okay, and we'll come back to that later. So this is talking about the CT. The next part talks about the significance of CT location. So I'll talk about that when I come to it. But in general, we have this. At medium voltage and low voltage, where do we locate the CTs for any purpose? For metering, for protection. We have two sides. We can either locate the CTs on the bus bar side of the breaker or the line side. And in general, we will always locate them on the line side. But for 375 kV or transmission, especially outdoor, you can also do that. Do we locate on the line side or both sides? For distribution, for medium voltage, we only use one side. But for transmission, because especially the outdoor switchgear, we can locate on two sides, line and bus bar side. But in general, you find that we locate them on one side. And when we locate them on one side, it has an impact on our protection zone. So we'll talk about that. That is significance of location of CTs. Then we will, there are actually other notes, but in between, but we'll come to that later. Then we talk about how do we protect transmission lines. So we're going to use current differential relays for transmission line. But in the good old days, we use something else called a pilot wire protection. Now, I'll just show you the very basic idea of pilot wire protection. This wire, I would think that this relay is no longer in use for new projects. So if anybody got any questions regarding this old relay, I'm sorry, today I don't have enough time to look into it. Maybe I can, if you're really interested, I'll try to find some time to discuss this with you. So we're going to talk about differential protection for transmission lines and for cables as well. And for this relay to work, we need a communication link. And what do we use for this communication link? What happens if the communication link fails? Okay, that's the easy part. The next relay is more complicated. It's called the distance relay. Now, what has happened is that I've covered distance relays earlier under one of the sessions called directional protection. But now I go deeper into it. Okay, so we'll talk about the principle of differential relay, this distance relay. At one time, the distance relay was the kingpin of transmission protection. Why? Because there's no other protection that will work. That was the best protection. Okay, but now with the current differential relay, with all these optics and fiber optics and so on, the distance relay has been demoted. Now it becomes only a backup. But although it's a backup, it plays a very important role. And we'll look at the different types of, the different characteristics of distance relays and the settings, the difficulty of setting some of them. And you can go in very much detail into this distance relay, but I only will give you a general idea of what distance relay is all about. Okay. So we'll look at the settings. We're going to call them zone 1, zone 2, zone 3. We will use the term underreaching, overreaching. Okay, so we'll look at all those. And then the last topic that we'll deal today is bus bar protection. Bus bar protection essentially is a very simple thing. It's a differential relay protecting the whole bus bar. The problem is your bus bars can be divided into 3 sections. You can have a main bus, you can have a reserve bus. And the main bus can be divided into the left side and the right side. So you can say there are 3 zones. So what happens if you have a bus bar fault in any one of the zones? You do not have to say, I have a bus bar fault on the reserve bus and I trip everything on all the main, all the reserve. That means you have lost a lot of circuits and you have tripped a lot of breakers unnecessarily. So what we then do is we arrange protection in such a way, if there's a fault in one zone, it will only trip that zone, the reserve zone, for example, the reserve bus, or the main one, a part of the main bus bar, or the main two, part of the main bus bar. And to do that, that means we need a very complicated protection. We need to have things called discriminating zone relays. And to make sure that these relays trip really for a fault, we need to have a check zone relay. A relay that says, hey, you think there's a fault? Yes, I confirm there's a fault before you can trip. Remember the logic, and that's what it means. So bus bar protection can be very complicated. And now the traditional bus bar protection relays have been what's called a high impedance relay. But nowadays there's available something called a low impedance relay. And low impedance relays, I'm not that familiar with it, but the good thing is I have a few CRP relay manufacturers with us, and I'm sure if I run into any problem, I can ask them to help me out because I have no hands-on experience with this low impedance. So that's what we'll cover today. And at the end of it, I hope to find enough time to be able to do the quiz. Okay. Okay. Are there any my PowerPoint slides? Guys, are you able to see my PowerPoint slides?
Cannot.
Cannot. Okay.
No, we can't yet. You haven't.
Cannot, is it? Okay, let me go back. I thought I put to I should put to desktop. No, I should put to desktop, right? Win. I got desktop.
Screen.
Huh?
Oh, you see desktop, is it? The word desktop.
I saw desktop at a window.
Then desktop. Desktop is
desktop. Okay. So are you able to see my PowerPoint now?
Yes.
Okay, thank you. Who is that, by the way? The voice is very affirm. Sounds like Albert, is it?
Chua.
Sorry?
Chua.
Mr. Chua.
Chua. Oh, Chua.
Yeah.
Sorry. Your voice sounds very different, Chua. Okay.
Oh, yeah.
Okay. So today we're only going to cover about 90 slides. Hope I can finish them. Okay. And the next session we'll cover another 90. Yeah. So let's look at the topics. So these are the topics that we'll discuss. And as you can see, I've added some additional notes. So we're going to talk about protection philosophy, and I'm going to talk terror system operation. Okay. I'm going to talk about significance of location of cities for short circuit protection. I'm going to talk about protection of transmission systems. So we're going to talk about the unit protection of lines and cables, talk about distance relays as a backup, and bus bar protection. And the next topics we're going to leave for next week. So we'll talk about the operation of main and backup protections, breaker failure, bus separation, auto reclose. So today we'll just talk about the first few topics. Okay, so let's talk about philosophy. So philosophy is a term we use, like the concept of what we're going to do, and terror operation. So this is a repeat of what I told you earlier. Now, at high voltage transmission, every piece of equipment has to be protected against faults by a unit protection. Unit protection, in case you don't know, refers to a differential relay. And the differential relay is the fastest relay that we have. Okay. And the fault clearance, if you use any slower relay, you may have a system collapse. So we don't want that. We cannot say, I got a bus bar fault. Let me save money by putting an overcurrent fault relay. Cannot. The system collapses, you're in trouble. Not worth it. And the backup protection is by distance relays. And then we also use other relays called breaker failure. But in older systems, you may be using overcurrent fault relays, which is very much used in other levels. So there's a high voltage level transmission, and medium voltage, we're talking about distribution, industrial. Okay, the more important equipment. So some equipment are protected by unit protection, differential relay. Some are not, and the most obvious one is the bus bar protection. The bus bar. The bus bar is very important, but they are so rare. Bus bar faults are so rare. We say, never mind, let's go and put in overcurrent fault relays. The overcurrent fault relays for the incomers are the main protection. Of course, nowadays we have other things like what we call arc flash monitor, arc flash protection and so on. But in general, for a lot of equipment, we only use overcurrent fault relays. Okay, and smaller transformers, we also protect them by overcurrent fault relay, and that's it. Okay, and the backup is also by overcurrent fault relays. So we can see the importance of overcurrent fault relays at medium voltage, but at high voltage, essentially it is of no use. Okay, of course, low voltage, you know lah, we just want the cheapest protections, we just overcurrent fault relays. And this is a very simple drawing. So you can show that each piece of equipment has its own zone of protection. I didn't put in everything, otherwise it gets a bit complicated. So you can see, for example, you have this, we have CTs all over the place. So you can see there are two CTs. We'll explain why there are two CTs. So you can see this is the bias differential relay for transformer. Okay, from the first CT until the last CT. There could be other CTs which is not shown now. Let's to avoid complications. This is for transmission line. You can see we have two sets of CTs here. We have two sets of CTs there. And between the first and the last, we then have a differential relay. So we call this the current differential relay. Now, in distribution, we don't have special protection for the bus bar. But in transmission, we have a bus bar protection relay. And here you can see we have two zones. We have one zone, let's call it main 1, and let's call it main 2. So if we want to put in the bus bar protection, the cheapest one is to put in one bus bar protection for everything. But that would mean that if there's a fault here, I would trip everything. So instead of doing that, we spend more money and we divide the bus bar into two zones. So let's call it M1, let's call it M2, and we need more CTs, we need more relays. So there's a fault for, there's a bus bar protection for this side, there's another one for the other side. As I said, I didn't put in all the zones, but just to show you the concept. And you can see there must be an overlap. Okay, there must be an overlap. So that technically speaking, if there's a fault here, both relays will see. But there's later on you will find there's a problem with regards to this CT location. So we'll talk about a bit later on. So these are overlapping zones of unit protections. What are unit protection? We use a different equipment. So medium voltage, we use differential protection. Okay, it's provided for 33 kV in general, and sometimes for 11 kV. Okay, and in the case of HV-MV, so HV will be, say, for example, a 275 step down to 132 kV transformer. HV-MV could be 132 step down to 33, or 275 step down to 11. Okay, so in that case, you will use one or two differential relays for the transformers. But when do we put in? Because we're not going to put in for any transformer. So in general, somewhere above 5 to 10 MVA, then we start considering putting in a differential relay. What happens to MV to LV? So 33 kV step down to 11, or sorry, 30 kV step down to 415, which is very common nowadays. So you just use overcurrent fault relays. Or in certain cases, we just use fuses as part of a ring main unit. Motors, of course, we need, I'm not going to talk about motors, we'll talk about generators, LV equipment, and bus bars. So if it's a high voltage, then we need to put in a differential protection. But low voltage or medium voltage, we just put in overcurrent fault relays. That's it. By the way, if anybody got any questions, stop me anytime. So now we come to redundant protection, duplicate protection. So in general, up to 132 kV, you're only protected by a single main protection. That's it. We depend everything on this one protection, exactly like what we do at 11 and 33 kV. But anything above that at EHV, that is not good enough, especially in the utility system supplied by Tenaga Nasional, Sarawak Energy, or Sabah Electricity. So what they do is 275 and 132 kV system, in general, we're protected by redundant main protection, but they must be of different mix. We don't want them to have the same mix for obvious reasons. And then how do you treat them? So the arrangement for bus bars will be arranged as a what you call 1 out of 1, 2 out of 2, or 1 out of 2. So we'll show you in a little while. Okay. And now remember I told you about the 100 milliseconds. So why do we clear a fault in 100 milliseconds? And the answer is we need time for the relay to work. We may need time for tripping relay to work. And finally, we need time for the breaker to trip. Typically, that's what is shown here. In other words, a breaker, once after getting a signal, does not trip in 0 milliseconds. It takes about something less than 3 cycles to operate. So we have 20 milliseconds for the main protection, maybe another 20 milliseconds for any tripping relays, and then another 60 milliseconds for the breaker. And that 60 milliseconds is called the breaker breaking time. So let's look at the different tripping arrangements. So you can see what happens if you have only one relay, then one relay trip, that's it lah. But what about two relays? How do you arrange them? So you can see I have two relays. I can arrange them as a logic OR. So if this relay trips or this relay trips, we will trip. So these are totally redundant in the sense that they have different DCs, they have different ACs. If you have VTs, they have different VTs. So totally independent. But of course, they trip the same breaker, and maybe the breaker fails, then that's a different problem. So that's a logic AND condition, OR condition. The other is a logic OR. So this one, we accept the fact that, hey, trip wrongly, too bad lah. And we accept that for transmission lines. Why? Because we've got so many transmission lines. So trip one wrongly, well, okay lah, some consumers may be affected, but we accept the risk lah. So what do we do if we don't accept the risk of wrong tripping? Then we arrange the two of them as a logic AND. That means both must trip together before we can get trip. But this is another problem, the opposite problem. What happens if one relay fails? Now we have no protection. So both have their strengths, they have their weaknesses. So what are you going to do if you have a system that fails to trip because one relay failed? In this case, the logic and condition. So let's go and see how we can improve it further. So how we can improve it further is at 275 kV. We can do two things. You can, in this case, I didn't do the whole thing, but actually you can put in 4 different set of CTs, okay, technically speaking now, with 4 different relays, and they are wired as a duplicate 2 out of 2, a redundant 2 out of 2. So can you imagine how many relays, how many CTs, and so on? So if any one relay, any failure, we are still okay. And we do that, we actually do that 275 kV for the bus pass. But if you want another one, this is called a 2 out of 3. I call it the parliamentary system, because in this case, you need a minimum of 2 relays to trip out of the 3. And if one of the relays fail, we are still okay. Why? Because it doesn't cause a tripping. And this is the same system that airplanes use in for their pilots. For certain some critical instruments, they have 3 instruments. One for the pilot, one for the co-pilot, and the third one like a spare. And so if the pilot has a problem, if either the pilot or co-pilot has a problem, he can switch over and say, hey, I want to get it from the other side. So the parliamentary system, of course, the way I understood it, probably we have to use it for nuclear power station. That's the way I understood it.
Okay, go back, okay?
Okay.
Go back.
Now we come to backup. I can hear a kid's voice. Can you please mute your mic? Thank you.
Finish this one. I do work, okay? But we'll wait for you. Just like the.
Okay. Okay. So now we come to backup protection in transmission systems. So traditionally, we always use overcurrent fault relays, and that has served us well in up to distribution, but it's of no use in transmission, right? Why? Because of the interconnection. We have so many para in phase, so many multiple para paths. It is impossible to define clearly what happens during a fault. You cannot grade them. And even if you can grade them, they are too slow because they have got this inverse curve. Okay, so what do we need? We need to have another relay. And in general, the only relay that we use as a backup, one of the main relays that we use as a backup is going to be the distance relay. And the distance relay is going to use a definite time relay. Definite time means after the relay picks up, after a certain set time, which is fixed, 0.15, 0.3, it will trip. So that's the difference between transmission and distribution in terms of the backup protection. Okay. So the alternative in servicing this is to, number one, use a distance relays. The distance relays use a backup for lines and for bus bars, because Funnily enough, the bus bar is a very important part of the system, but it has no backup protection by itself. In other words, a transmission line, it fails, we have a distance relay as a backup. A transformer, it fails, we have an overcurrent as a backup. But the bus bar protection, when it fails, there's no backup locally. The next backup will be at the transmission line, transmission line. And that backup is actually at the remote end of the line, which I'll show you in a while. So we can use distance relays as a backup. And distance relay is very important for that purpose. And then we also use distance relays as backup protection for very big transformers. I'm not familiar with it, but I see in the TMB drawing, they use a distance relay as a backup for this 500 275 kV transformers. Okay. And then of course we're going to use other protection that we have just mentioned this morning. We're going to talk about breaker failure, and we have this bus separation scheme, okay, to try to prevent a big tripping. And then the zone 2 of the distance relay typically has a time delay of about 300 to 450 milliseconds. We'll come to that later again. So trip circuit supervision, I won't talk too much about it. I said to mention, hey, what happens if the trip circuit fails? What can happen to the trip circuit? Okay, well, the power supply can fail, the trip coil can fail, in the sense it becomes an open circuit. And then of course the wiring itself, maybe there's something wrong with it. So to make sure that the trip circuit is ready to trip, we have something called trip circuit supervision relay. And in general, we use dedicated relays for that purpose. But actually, if you want to, you can. There's another way to use a cheaper alternative. So overview of transmission protection schemes. So now let's look at the overview. So we have two types of protection. One is an equipment protection, and the other is what is called, I call it a system protection. So let's look at it. So cables and lines, we're going to use a current differential relay, and the backup will be a distance relay. And that's one we're going to spend the next 2 hours talking about. Then at the end of it, you're going to talk about bus bar protection. So sometimes we have 1 up to 132 kV. Then for 275 kV and 500, we have a duplicate protection. But the funny thing is there's no local backup protection. The only backup protection is at the distance, which may be at the other end of the line. Transformers, of course, we have a lot of protections. We have bias differential, and in the case of 275 kV, TNB and SCB, sorry, they all require duplicate. But for the consumers, we don't do that. It's too expensive. Then, of course, we got things like restrictor for protection and so on. And then we have overcurrent of fault relays as backup. Okay, so of course, we are not going to talk about this topic today. Then we have breaker failure. So breaker failure is to trip the, there's one for every circuit. So if you got 5 circuits, each circuit has its own breaker failure relay. So you will detect that there's a fault and somehow the breaker didn't trip, and then it will then trip as if like it's a bus bar fault. We'll talk about that later. And okay, so just a note that in transmission system, a reminder that we don't have ITMT overcurrent relay for cables and lines and bus bars. Okay, we don't have that. Okay, they're too slow. It's a reminder. And the last one is what I call system protection, in the sense that there is a failure this time of the protection itself. So if we have 2 incomers and either the main protection fails, then both incomers will trip. But we don't want that to happen. So what we do is we use a bus separation relay to break up the system by opening the bus section. So that one side will see the fault, the other side doesn't see the fault anymore, and we limit the amount of tripping. That's what we mean by this bus separation scheme, which may not be practiced by all utilities. Then what are the other additional things that we need? We need synchronizing. So I won't go too much into detail, but in general, every transmission substation has what's called a swing panel. So swing panel will include all the synchronizing facilities, and you also need what we call this synchronizing or a sync check relay for the transmission lines for auto reclose purpose. So that is synchronizing and auto reclose. But I won't cover this, especially the synchronizing part. I won't cover it because it's just like any other synchronizing. Now we come to this problem called parallel operation, interconnected operation. Is it good or is it bad? Of course, parallel operation is good, right? It gives a better reliability. There are some advantages, but the main advantage is better reliability. I have two lines in parallel. There's a line fault. I lose one line. The other line is designed to carry the whole load. So very good. But it can give rise to problems. Okay? Because you now have two parallel paths. So two parallel paths mean what? What happens during a fault? Let's look at it. So this, by the way, okay, I'm going to tell you what this drawing is very important so you understand what it means. Number one, this is the utility system. So we have a feeder, two supplies coming in. So we have what we call a bus bar with two sections. So main one, main two. Two cables coming in, go to this. I call this an H arrangement. Why? Because it looks like the letter H. A 5-circuit H arrangement. Incoming line, outgoing to transformer. Incoming line, outgoing to transformer, and in the middle we have a bus section. So it looks like the letter H. This is the most common arrangement for consumers taking supply at transmission level, especially. Then, how do you operate this system? In general, you might say, hey, I want to close my bus section here. But before you can close this bus section, you must make sure that this bus section is closed. Because if you close this without closing that, there can be some problem, which I'll tell later on. So now we have A bus section is closed, B bus section is closed, everything is closed. I didn't put a bus section here, okay? So everything is closed, the two systems are in parallel. Very good, right? Why? Because if there's a fault on one line, the other line can carry the full load. I'm still okay, very good. But the problem is, what happens if the fault on one circuit and that breaker either fails or the relay fails? Either the breaker failure or the relay failure. So let's take the case of a simpler case of a relay failure. So we have a fault here. This relay fails. So you cannot trip. Can it tell anybody that it has failed? It has failed, so you cannot tell anybody anything. So all this will see, hey, there's a fault current. So how many fault currents are there? There are two fault currents. One coming through the upper cable, another going through the lower cable. So where is the protection? The backup protection must be somewhere on these two lines. And they both see the same current. They have the same settings. What happened? They both trip at the same time. So now we have a fault. Now the parallel system, instead of trying to help you, now the parallel system makes things worse. Because of this situation, which is very rare, but you have lost two incomers because of a single event. That's not acceptable. So what do we do? What we can do is we can put in something here to detect that, hey, there's a current coming in here flowing for too long. In other words, there's a fault, there will be a current coming in. But the next moment, the fault disappears. Remember 100 milliseconds? 100 milliseconds, the fault disappears, this fault current disappears. So no problem. But assuming that this says, hey, I see a current more than 100 milliseconds. So I know there's a fault. What do I do? So we have a bus separation scheme that can then trip this. So if we trip this, what do? You're splitting the system into two. One healthy system with no more fault, one faulty system with a fault, and of course, finally, you got to trip this system. But now you have lost half the system instead of the whole system. So two events can happen. One is the relay can fail, one is the breaker can fail. And this sort of thing can happen for any fault. It can happen for a transformer fault. It can happen for a bus bar fault. It can even happen for a fault here. For the fault in this line, what happened? There's a current coming this way. There's another current coming this way. And if this relay fails, we are in trouble. So what do? So we have to find somehow, if possible, try to switch off this. So parallel operation has its advantages, but there are some drawbacks. That's what I'm trying to tell you here. Parallel operation, okay, as shown in the next slide, requires parallel parallel of the upstream bus bars. So in other words, before you can operate the transformers in parallel, the system upstream must also be in parallel. If you don't, I'll show you the problem. Okay, and the fault of the main protection during downstream fault. So the downstream fault, internal fault, if the main protection fails, if the main protection works, no problem. But if the main protection fails, we have a problem because the fault current will trip both incomers. So you then need special protection to split the system. So we need something called a bus separation scheme. Okay. And the other problem, and what happens if you didn't operate properly? In other words, if you didn't operate properly in the sense that if you have two transformers, there are cases people, for example, operate the system with the two transformers. They're parallel here, but the two transformers out of step. And out of step, you create another big problem. And I know somebody who has a big bill problem, somehow related to this circulating current. TNB is charging him a massive bill, and I don't know what they're going to do. Now, another problem would be this. Okay, what happens if there's no fault? No fault, we shouldn't have any problem, right? There is a potential problem. And my friend tells me this has really happened. You remember I told you, if you have this sort of system, before you can close in this, you must close in this. So I'm not talking about faults now. So this has nothing to do with fault. This is just for information only. Okay. What happens if you have a load? So your loads will come this way. Your loads will come this way. And essentially, the current here will be zero, right? Where are your meters? The energy meter, the revenue meter, they are here. The meters are always on the incoming side, not on the transformer. They're always on the metering side here. Now, is it possible for some unknown reason to you, outside your control, this breaker is open? And you don't know because this belongs to the utility, but this breaker is open. So let's look at the system before the breaker is open. Now, this is a TNB system, utility system. So the utility system is feeding power to the consumer. So it comes here, it feeds into this one, it comes here, it feeds into this one. So we have two equal currents flowing into these two equal paths. So the current here should be zero. But this is also part of the transmission system. So power can be coming in here and power can be going out here. Right? You can see here, P1 coming in, then this is going here and coming here. So in other words, if you look at it, you can look at this case 1. So case 1, the power flowing here will be P2 will be, this P2 is equal to P3 plus P4, right? So I'm going to fix some values. I'm going to say that for our purpose, we'll look at two cases. And both cases are based upon that there's a 40 megawatt coming in and 20 megawatt load. So 10, and the 20 megawatt export. So I put a minus here to show its export. So 40 megawatt comes in here, 20 megawatts exported, and then 20 megawatt goes to the load. Very simple, right? Is there a possibility, without your knowledge, for some unknown reason, TNB opens this, probably by mistake? The interesting thing is, what happens to your load? Your load is still there, no problem. Current comes in, I got power here, feed 20, no problem, why worry? There is a potential problem. Why? Where is this 20 megawatt going to come from? And the only way that 20 megawatt can come from is to flow through here. So now this one will import 40 megawatt to supply everything and export 20 megawatt. That's shown in case 2. So are you with me? 40 megawatt comes in, 40 megawatt comes in, 20 megawatt goes to the load, 20 megawatt goes to the TNB system. So your system, the consumer system, has now become part of the utility system. What happens to your billing? Your billing will say, hey, I'm importing 20 megawatt, and importing 40 megawatt and exporting 20 megawatt. What happens now? Technically speaking, what happens is TNB should have what's called a 4-quadrant metering. That's stated here, 4-quadrant metering. That's able to measure, hey, I got power coming in, I got power going out. So the net power is 40 minus 20 equals to 20. But if TNB doesn't have this net metering, this what they call 4-quadrant metering, maybe some old stations, I don't know, you have a problem. And according to what I know, this has happened somewhere. I can't remember where. One of my friends tell me a project either in Bandar Utama or somewhere in Malacca. And so you better make sure, if you are responsible for a project like this, you better make sure you have a digital power meter that's able to record this, just in case in other words, your digital power meter must have this 4-quadrant metering. Just in case TNB's meters, they are not able to record it, at least you got to prove. And you can say, hey, look, my metering shows that this is what came in, this is what came out. Therefore, your metering is wrong. Please pay me back. Because if you don't have proof, then you have a big problem. So this has nothing to do with protection, but I thought I should just share with you that since I heard that if somebody really had this problem, I thought I'd just share this with you. So any questions on anything we've discussed so far? No questions? I'm surprised. Okay.
Yeah, Mr. Kennedy here. The direction for P3 should be reverse, right?
Yes, that's why there's a minus.
Minus. Okay.
The minus tells you is reverse.
Okay.
Because
yeah,
you
last
can
time
see
I think Sun Power, one of the station there was some issues like this.
Do you remember which station that was that, Kennedy?
I think you're not mistaken, Sun Power.
Sun Power, maybe. Also, it's either Malacca, Sun Power is Malacca, is it?
Malacca, yeah.
I think that must be the case. Yeah. You can see, for example, if I put P6, P6 normally will be coming in this way. But when this is open, P6 will be minus. You can see P6 has changes direction. P6 is 10 and then became minus 20. Because originally you're just importing 20 megawatt. Now it's exporting 20 megawatt to go out. So I keep direction the same. I just change the sign to tell you that it's an export. So thanks. So Kennedy just confirmed, in other words, that it's very rare, but who knows, it may happen. And actually, for any of you who ever operate what I call this 120 system in this way, you can actually, when you go and play around with this circuit breakers, you can actually see the reverse flow, which I've seen before. Okay. Any questions? Win, any questions from the floor?
Hello? No, not at the moment.
No, surprise, huh? Okay. Now we'll talk about significance of CT location for short circuit protection. So this CT location has nothing, is not important for metering, it's not important for load flows, it's not important for a normal condition. It's just for short circuit protection. Why? Okay. So now we're going to go back to medium voltage. So indoor equipment, AIS. AIS, in case to those who don't know, means air insulated equipment. Your normal 11 kV switchgear, your outdoor switchgear in the TNB transmission system are air insulated. Of course, nowadays we got this GIS, gas insulated. So CTs for indoor equipment are located on the line side of the breaker. Why do we locate on the line side? We can always locate on the bus bar side, right? But we never do that. Why? A few simple reasons, technical reasons. Number one, if you want to do any shutdown, any work on the CT, you don't have to shut down the whole bus bar. For example, hey, I need to change the CT. It's located as part of the bus bar. Shut down the bus bar. Very inconvenient. So I can easily locate it, switch on my circuit breaker, rack out the breaker, and I can start work. Very easy. Now, what happens if I put in the bus bar? Now, the bus bar is a very important part of the system. Very, very important. So do you want to put in as many things as possible or as few things as possible? Obviously, the less you put in, the less problems you're going to have. So why you want to put in CTs inside there? If something goes wrong with the CTs, we have a big problem. So let's minimize the number of components in the bus bar compartment. And if you look at it physically, the bus bar in the 11 kV switchgear, 30 kV switchgear is very, very small. So you don't have all this space. So indoor equipment, definitely CTs are located on the line side. Finished. But what about and then there are also CTs that are located on the bushings of transformers. To be honest, I never understood why they locate it on the bushing of transformers. So in other words, instead of locating the CTs at the switchgear, locate the bushing. Sometimes we need that for certain protection. But for differential protection, I never understood why they do that. Okay. So if you have located on the bushing of the transformer, you have a problem when you do primary injection, and if you have to change the CT, I think it's going to be a huge problem. So I thought that people don't put CTs in bushings, transformer bushings. So where can we locate CTs then for transmission projects? Outdoor equipment, let's say lah. So you can locate CTs at three different locations. You can locate them on the line side, you can locate them on the bus side, and you can locate them on both sides. So where are you going to locate them? And in general, we always locate them on the line side. For the same reason, if you locate here, if I need to change any CT, then I have a lot of work. So I try to locate them on the line side. Okay. But you can see, I can put them on the bus side. And then for the bus section, okay, for the bus bar protection, I need CTs. Okay, they must be on the lines, bus bar side lah. So the one I can't help it. Okay. So we have three choices. We can locate them. CTs on both sides, CT on the line side, CTs on the bus side. Okay. And what about generators? Generators have another problem which I'll talk to you about. You can locate them on the line side, you can locate them on the neutral side. So the same situation. Okay. So now what is the importance of this? The importance of this is, where does the protection start? If I locate them here, in other words, how many CTs do I need here? For a transmission system, minimum, from protection point of view, I need minimum of 2 protection CTs. One is for the bus bar, one is for the feeder. So if I put it here, then where does my bus bar protection start? You can see my bus bar protection is here. Remember I told you the bus bar is divided into 2 zones? So I got the left side of it, so you can see the bus bar protection will start from this CT, this CT, this CT, and end at this CT. So that is where the bus bar protection is. And then I have another set of CT that will protect the feeder side. So we have this one set of CT used for the bus bar protection, another one used for the feeder. Later on, you find there's a problem. Why? Because this part here is actually not part of the bus bar, but it's protected by the bus bar protection. That means that if there's a fault here, although it's not the bus bar, for protection point of view, it is the bus bar. It will then trip the whole bus bar. We have no choice. Okay, then what's the other problem? The fault is here, actually it's part of the feeder, but the feeder starts from here. So this is not seen by the feeder. This fault here is seen by the bus bar protection, but not seen by the feeder protection. And that's what is shown in the next drawing. You can see I put my CT on the line side. So I got 2 CTs. One for the bus bar protection. That's the outermost. It must cover as much as possible. So the bus bar protection will cover here. And the other one is for the line, and the line will cover here. So you can see there's an overlap. So what happens to the fault? You can have fault in 3 locations. Fault here is definitely part of the bus bar protection trip. Fault here is part of the line relay trips. What about the fault here? In the middle. The fault physically is part of the line, but the line protection cannot see it. It is not part of the bus bar, but the bus bar protection will see it. So for the fault here, we treat the bus bar, but we didn't clear the fault because the other side is still feeding into the fault. What can we do? Oh, I don't like this, I don't like this, I don't like this. If you put on the other side, you end up with a different problem, but essentially the same. That this is now part of the bus bar, but it's not protected by the bus bar. So we have, either way, we have a problem. So we have the general practice is somehow we'll live with this.
This kind of arrangement is this physically there are two CTs, is it, or
No,
it's sharing the same core?
No.
Different cores.
Okay. Who is that, by the way?
Kennedy here.
Kennedy. No.
Yes.
Physically, it is in what I call a CT stack. But inside the CT stack, actually there are maybe 5 different CTs. Okay, since Kennedy asked, I'll show the drawing. Oh, it's not part of this. Okay, it's in another set of notes. Kennedy, I'll answer your question later. But sure. What it means is physically there are, in this case, 2 different CTs. They're just mounted in the same bushing. That's all. There are 2 different iron cores. They have nothing to do with each other. One could be a metering CT. One could be a distance protection. One could be a bus bar protection. One could be overcurrent and so on. So there are different CTs physically mounted as part of the same physical unit. But inside there may be typically 5 different CTs involved. So after the break, I'll find a slide for you, Kennedy. And of course, you're really interested, then you come for the next course. Okay. So Kennedy, can you hold on for a while? Have I answered your question, Kennedy?
Mr. Lee.
For time being? Sorry, is there a question?
Yes, Mr. Lee, I'm Hazim here.
Hazim, yes.
From maybe. In reality, is it the blind spot, this blind spot space? Is it truly exists? Meaning, is it big enough for the fault to happen? Maybe in reality,
there will be a very short zone. Yes, there is. There's always a very short zone. It may be 1 or 2 meters, but it's part of it. So if it's a GIS, maybe this, maybe let's say, maybe I don't know, maybe let's say 1 meter only maybe I don't really know maybe even less. Okay, but there is it likely to be a fault here? The chance of a fault happening there is very, very, very rare But
very rare, right?
Yeah. But we just you must be aware that there is this problem.
Oh, okay.
Okay.
Thanks, Mr. Lee. Yeah.
Okay. So let me see, is there any drawing I can show you? Unless I'm going to look at the layout drawings, then only I can show you but there it actually is there. Okay. Any other questions? Of course, then what happens if you say I want to put CTs on both sides? Can. So you can put CT on one side here and CT on the other side. You have put 2 sides. Of course, then spend more money. So you can put say, hey, I have this one that is part of the bus bar, and I have this one that's part of the line. Can. But you need to spend more money because not only you need more CT, you need more bigger substation, you need more foundations and so on. Can. But I don't remember offhand whether anybody ever use it. If anybody has, let me know. But I don't remember. And then in that case, of course, any fault between these 2 will then trip everything. Fault here will trip the feeder. Fault here will trip the bus bar. Everything will trip because this is an overlapping zone. It's seen as far as protection is concerned. It's part of the bus bar. It's part of the feeder. So it trips everything. So any questions?
Mr. Lee?
Yeah, who's that, please?
Yen Yi.
Yen Yi, yes.
Okay. Normally we are using the option A2 for the city location.
Yeah.
I would like to ask if let's say TNB metering, just now the A2, yes, A2.
Yes. Okay.
Another. The common one, the common location.
Anyway, now what was the question? Anyway, I know.
Next slide, next slide.
Oh, sorry. Okay.
Yes. So TNB metering request, the metering city, P1 must be facing the incoming city.
Okay.
P2 is the end user.
I don't know why they make. I know what you mean because Yan Yi and I are both involved in the project. I to be honest, I don't know why they even mention it at all. I'm totally puzzled. I have no idea. So we can discuss that separately, Yan Yi, because nothing to do with it. But
Okay.
To me, it's what they call a moot point. What was so because polarity is a polarity problem. Polarity just reverse the secondary wiring to solve whatever problems you have. So and that project, that's what has been proposed is standard for all other projects that I've seen. So anyway, we discuss it separately.
Okay, thank you.
Okay. So any other questions?
Mr. Lee, Chung here.
Chung, yeah.
In most of the case, we are using option A2, right, in Malaysia?
As far as I know, yes. Yeah, go on. Is there a question?
No.
Okay. So in other words, where is the most likely location? Most likely is on the line side lah. Together, similar to your. So the good thing is just remember where is your CTs on your 11 kV switchgear? You open the cable box, you see the CT somewhere inside there. So we do exactly the same thing for the transmission voltages. Okay. So sorry. Where am I? Okay. So option A1. So basically just saying the same thing about overprotection, underprotection. So I think I hope you understand the concept. Of course, then this is so you have two choices. Do you want to put it here on the line side or the bus side? So whatever you do, you have a problem. Okay. If you put here, then it doesn't protect. This is not protected by the feeder. If you put it on the inside, then this is protected. Will trip this fault here will trip the feeder protection. So I use the word under protection, over protection. That's all. Okay. So ideal protection will be from circuit breaker to circuit breaker, but we can never do that unless we have some very switch gear, which we have actually 1130 kV. We put the CTs in the circuit breaker bushing. There are CTs that breakers that allow you to do it, but only 1133 kV. Talking about outdoor under and over protection.
Ali.
Yeah, who's that, please?
Shamsul.
Shamsul from PNB generation. Yes, Shamsul.
Okay, when the blind spot happens, so the main the unit protection will not clear the fault, right?
Okay. Maybe you can refer to one particular slide, then easier. You can refer to this one.
Okay. This
one. When it talks about this blind spot, it's saying that as far as this is concerned, the feeder protection will not see it, but the bus bar protection will see it. So it's blind to one, but over protection by the other one. So it is seen by a protection.
Okay. So this one.
Are you with me, Shamsul? So now, where is your feeder protection? Your feeder protection will start from here.
Okay.
Let's take the case that we have been talking about here. Your feeder protection starts here, right?
Okay.
So, but physically, actually, it's part of the feeder, right or not?
Okay.
But can the feeder protection see? Cannot. So for the fault here, the feeder protection cannot trip. So what will trip instead? The bus bar protection will trip. So the blind spot in that the wrong relay trips but it is still protected by a protection. It's not blind in the sense that there's no protection. So the word blind spot is not my wording but that's the only wording we can find. And these are two from some others notes So it's a blind in the sense that the wrong relay trip, so to speak But in this case, probably not a problem Why? Because if the bus bar protection is tripped, this is obviously whether it trip or not so critical Okay.
If this breaker is connected to the generator, so we still have the fault, right? So the fault is not clear.
So the question then would be, if there is a busbar protection trip, should they trip the other side? Which you have to decide later lah. For example lah, okay, later on as I said, we're going to talk about busbar protection. So if there is a busbar tripping here, we have tripped this. Do you want to send a signal to trip the other side? You can obviously. But from what I'm told, correct me if I'm wrong, we've got a few guys from relay manufacturers. So from what I am told is that we don't do that. If there's this one bus protection trip, we hope that the fault is not here. And the fault is here, then too bad. Then we have to wait for something else to trip. But technically speaking, yes, we can say, I have lost my bus bar just in case the fault is here. I must have tripped the other side. But that also means there's a problem. If you got 4 lines coming in and now you lost this whole bus bar and then you trip the other 4 lines on the other side, wow, the GSO people will be very confused. Hey, how come I got multiple trippings all over the place? This substation lost 4 breakers. The other substations lost 2 breakers each. Wait, what's happening? What's happening? So that's where the confusion is. So what TNB does is, from what I know, is if there is a bus bar protection trip, it doesn't trip the other side. But if there's a breaker failure trip, it will trip the other side. Anybody from relay manufacturers, CRP? I got ETD and I got Brownfield. Faiz, you ingin memberi jawapan? No? Okay, Frederick, are you online, Frederick?
Hello, Early.
Sorry, hang on. Frederick, are you online?
Yeah.
Okay, can you answer the question? Does the bus bar protection trip send into trip to trip the other side?
Usually no. The tripping to remote end will only happen when breaker fail.
Yeah.
Breaker fail,
So,
send tripping
okay.
to bus bar protection and then remote end.
Thank you, Frederick. So what Frederick said is, for the bus bar fall, we don't trip the other side. But if the breaker fail, then we trip the other side. Send a trip signal. And the other side means you can also trip, like in the case, for example, in Brunei, we did a project called Lumut Power Station. So we have this bus bar protection. So when it trips, as far as I remember, Hafiza, you can confirm that, it will send a signal to trip the generator and its turbine and field and so on. So it depends on what you want. Do you want or you don't want? Up to you. As I say, you trip is good, but it can cause confusion. Because as I said, the GSO people would like to have the minimum tripping. I mean, I would imagine that you don't want to have so many alarms going on at the same time. You get confused. So you want the minimum tripping. But so if you have the minimum tripping, then don't send. But like what Frederick said just now, for bus bar fall, the procedure in TNB is don't send trip signal. But breaker failure, something has gone wrong, then let's send a trip signal. So have I answered your question, Shamsul?
In this case, if 87B cannot clear the fault, and 87N also cannot clear the fault, so we need to wait backup protection, right?
Yes, then we need to wait for backup protection. Yes, you're right.
Okay.
Yeah, you have no choice.
Okay, thank you, Ali. Okay. Right.
Yes, you have no choice. Yeah. So what Shamsul said is, what happens if this is a line and there's a fault here, and we didn't clear the fault, we only trip this breaker. So what happened is there's a distance relay. This distance relay will clear the fault. In the TNB system right now, from what I know, is about 415 milliseconds, which is very long, but actually can be reduced, but that's what we have at the moment. So there is a backup protection, and that backup protection should be pretty reliable. But for a generator, then different. Generator, then you have to depend upon other relays called what we call distance protection. And to be honest, I have no experience with setting this distance protection for generators. So I'm not very confident whether the relays will trip properly. I don't really know. Okay, Shamsul, have I answered your question?
Yes, Ali. Thank you.
Thank you. Any other questions? Okay, so this is a repeat of what I told you. Just so the word term over and under is intended to mean that the unit protection relays is covering beyond the limited zone. It doesn't mean there's no protection. It means that as far as that relay is a blind spot, but there's another relay that will take care of it. So it doesn't mean that there's no protection. So that you can see the ideal protection will be this lah. See, breaker to breaker lah. So in general, we put it here. That means there's this under protection here, or you put at the other side, then the over protection there. So no perfect solution.
Mr. Lee, for that slide,
Raman, is it?
Raman, yeah.
Raman.
Yeah. Then where would be the distance relay city location?
The distance would be the distance relay would be together with this lah.
One on each side lah.
One on each side.
So another city lah.
Another city of course. But this is the main protection. You're talking about a different city, yes.
Okay, understand. All right, thanks.
So now you see the importance of city locations, and that is more so. Shamsul, this is more related to your area since you are a generation man. Where do you put CTs for short circuit protection in the generator? Do we put on this side or do we put on that side? I'm talking about things like
for the backup impedance. Usually we put on neutral side.
Neutral side. Okay.
Yes.
Okay. I will tell you that whatever you do, there's no perfect answer. Okay. So in other words, we have two possible locations. And we can put it in an overcurrent fault relay. Overcurrent, in this case for generator, we call it 51V. Don't worry about the V. It's an overcurrent relay. That's all you need to do. So anything related to short circuit, not load, not unbalanced, not negative sequence. Or you can put it to a distance relay, 21Z. So we have two possible locations. So where should we put it here? Should we put it here or should we put it there? What's the problem if now? I don't know whether you're aware, but anybody who does medium voltage will tell you that the CTs are located here for the generator. If you got say a 3 megawatt generator, the CTs are located here. Right? They are never located there. Why? Because the generator manufacturers got no space for you to put in this CT. So we put in this here, and we are happily we say, oh, my generator is protected against short circuit. Ask yourself this question: what is this generator intended for? Let's take a case that this is a standby generator. So if it is a standby generator, that means it's never synchronized. And if it's never synchronized, what can happen? If there's a fault, if there's an external fault, of course the current flows through here. But remember, this is a standby generator. It's not synchronized. What happens if you have an internal fault? If you have an internal fault, the current flows here. So what happens to your protection? You will never see the fault because there's no fault current coming this way. So if you have a standalone generator, then where should you locate it? You should locate it at the end. But as I said, we have a problem because small generators, they don't have space here for you to install the CT. So I've seen cases. What they did was from this neutral cable box, they broke it up and took 3 cables and go into what's called a cable box. So they go into a box where they locate CTs. So that was what was done. So when you have a standalone CT, you must locate here, like what they say here. But what happens is synchronized? Synchronized, maybe you like to put it here. What happens maybe is during starting it is standalone, but during running it is what we call synchronized. Then what do? So you have 2 choices. So up to you which way you want to do. You want to locate it. As you can see here, this neutral CT can only see internal fault, the arrow direction. This CT here can see both internal and external fault. So be careful. And this also applies to the distance relay that we apply for the standby for this generator. Actually, if you look at the drawing for the protection drawing for a generator, it doesn't tell you whether the CTs are located here or here. They don't tell you. So if you really want, you got to ask the manufacturer, what is the purpose of that protection? Is it to protect the generator or is it to protect the transformer? So you got to be very careful. So that is on generators. And then the last one is on earth fault for transformers and generators. So you can see there are two locations for generator or this transformer earth fault. One is located on together with the line CTs. So these three CTs go into the earth fault relay. Another one is a neutral CT. So which will give you a better zone. To protect this one will see a bigger zone of protection. Why? Because this one can only operate for an external fault, assuming the radial system. If the radial system, this can only operate for external fault. It can never operate for internal faults. And this one can operate for internal and external fault. So this fault relay is not protecting the transformer. It's protecting the bus bar, the feeder. This one protects the transformer. And this is what we use when we have a standby fault relay. So a standby fault relay, we always use a neutral CT. So this just shows you the importance of CT locations for short circuit protection. In this case, it includes a fault. So any questions? Wow, it's 10:30, yeah. So, okay, any questions? Win, any questions from the floor?
No, not at the moment. Maybe I take a break for the video, then
Yes.
I continue here.
Thank you. So, okay, we'll take a 5 minute break. And then when I come back, I will try to answer Kennedy's question about CTs, okay? So 5 minutes, huh? So I'll put some music on. So when the music stops, then you know that yeah, we are back online, yeah? Okay, 5 minutes, okay.
Mr. Lee, a quick question.
Before that, okay, Chung, you got a question.
Can we have both protection at the bottom there?
Come again, you talk about this drawing?
Yeah, this drawing at the bottom is can protect external and the internal.
You mean, can we have both this and this?
Yes.
Of course you can. We do that all the time. For our 3311 kV transformer, you have 3311 kV, then you have a neutral earthing resistor. So you have your IDMT overcurrent, so which is used for overcurrent, and we have a earth fault relay here. At the same time, we have a standby earth fault, so it's here. So whenever you have a 3311 kV with the NER especially, we have both. We have this plus this.
Okay, thank you.
If do you need me to show you the drawing, or you're okay?
I'm okay.
Yeah, okay. Okay, so I'll put some music on, and then in about 4 minutes or so, we will continue. Oh, of course, anybody got any question can still ask while I'm doing. Anybody any other questions? What is the music program called? Like now I can't remember the music program. Okay, never mind. Spotify, sorry. No. Mm. Okay. Don't know why the music stopped playing. Okay. Win, are you back, Win?
Yeah, I'm here.
How many people have we got?
113. 14.
113, so about 20 people didn't show up. So I hope you're taking attendance, Win.
It's the auto record. Yeah.
Okay, thank you. Okay, Kennedy, are you on, Kennedy? Kennedy?
Yes, please.
Okay, so you can see here, this is to answer your question about the CT cores. So this means there are different ion cores. So in this case, for a typical line CT, we have got, how many cores have you got? 1, 2, 3, 4, 5, 6. Is that in, no, 2, 4, 6, yeah. Is that enough? No. Actually, there's, okay, so what are the cores used for? Okay, you can see this one. This is actually for a line. You can see there's a main one, there's a main two. So that's called a current differential main one, main two. The next CT, and that's got a very big ratio. The next one is got backup protection and got LI. And LI refers to a busbar protection called low impedance busbar protection. So there's another CT. The fourth CT is meant for your internal instruments. So this goes to your digital power meter and so on. And then the fifth and sixth CTs are meant for your busbar protection. This is a high, what we call the high impedance busbar protection. So you see this later on when we do busbar protection. So remember we need two CTs. So we have two relays and two CTs. So we have two for the busbar protection, two for main one, main two for the current differential. Then we have a backup, and then we have a metering. But this is not enough. Why? Because you need another set of CTs for the TNB revenue metering. and that one is actually shown as sometimes it's included here, sometimes it's another CTY, because there's a limited space. You cannot go and say I want to put in 20 CTs here. The length of the bushing to support this is limited. So and for other reasons as well, we have another set. We may have another set of CTs for revenue metering, and the same thing happens here. You see, this is the bus section. So the bus section, we have 5 CTs. Why? 2 for the main 1, main 2, 2 for low backup and low impedance, and 1 more I think can be for overcurrent, bus separation, that sort of thing. Of course, then if you really want, you can look at the actual CT lah. But this is just to show you the basic arrangement lah. So essentially, if you go inside there, you find that this one CT stack, that's another CT stack. Okay, and you can see here the P1, P2, P1, P2. So this tells you the PCT polarity. So have I answered your question, Kennedy?
Yeah. So like you said, I repeat again, this is one CT stack on the bus coupler.
So whenever you see a P1, P2, that means this is belong to one physically one unit of CT, but inside there are 2 iron cores.
Okay.
These are the 3 iron cores. So you imagine like your cable, like if your cable, inside the how many cable, how many CTs you need for the cable? You will need one for the differential. That's 11 kV lah, easier. You need one for the differential. You need one for the overcurrent. You need one for metering. Let's say lah. So you have 3 CTs. They're all stacked next to each other lah, but physically are 3 iron cores.
Right.
Can I answer your question, Kennedy?
Yeah, thank you. Yeah.
Okay, this is part of the drawing. So in the end, it might be easy, but just show you this lah. But if you really want to see more, then you have to go to a physical drawing of a CT lah. Okay, any other questions? I'm running behind time really.
Yeah.
Is there a question, sorry?
Yeah, there's one from Hyang.
Okay, yeah, Hang Jin Tong.
Why distance zone 1 need 150 milliseconds?
Okay, we'll come back later on. Okay. I have to ask his example okay, but I'll come there later on. So now I'm behind time, so I'm going to go through very quickly lah. So as I said, I told you the story that once upon a time the distance relay was a king of distance protection, of line protection. Now we have a new emperor, and that is the current differential relay. Why? The new technologies. Okay, but the distance relay can stand alone. But the current differential is what we call it needs a communication link. So that's called an optical fiber. And here I've given you some details of how the fiber is provided. I won't go into it. So it's essentially provided as part of the earth wire at the top of the transmission line. So transmission. For transmission circuit, we have current differential relays, which needs an optical fiber. Okay, distance relay, which doesn't need. We don't need that. But distance relay is now used as a backup. Current differential is a main protection. It doesn't do, it's like your normal bias differential relay. It doesn't provide any backup. Okay, it's 100% protects the line only. Okay, it's a main protection for lines and cables. Distance is 100% backup. It basically has no main function. Then of course we have for OA lines up to 33 kV, which are very rare in Malaysia. Sarawak still has quite a lot. I think Sarawak maybe we use overcurrent fault relay. And for cables, we use fuses, maybe in the ring main unit. Then, of course, for HVMV cables, we can use current differential again. Okay, and in the older project, we use pilot wire. But from what I know, probably it's no longer been made. I just might guess only. Then 11 kV, pilot wires are even less. Most of the time, as far as I know, PNB doesn't provide pilot wires anymore, except maybe for the first leg coming out from PMU, PPU. So, okay. So, the communication link is part of the topmost earth wire. So, I'll show you a drawing later on. Okay. So,
Mr. Lee, for that cables, is this for this transmission cable or also including the insulated cable?
Come again?
The distance protection for the current differential and the distance protection for the transmission cables. Is this just for the transmission cables or also including the insulated cables in long distance insulated cable, maybe 50 kilometer ke?
Yeah, you need it. For example, let's say between Pengerang to say the TNB, the nearest TNB, you got a cable maybe 1-2 kilometers. You need a power cable. You need an optical fiber. The optical fiber is generally separated.
That's okay for the fiber one. The distance one, I mean the distance.
Distance, no, you don't need. Okay, when we talk about distance, in the good old days, we have a very simple digital channel, but nowadays TNB no longer use that. So I'll talk about that a bit later. But in other words, the distance doesn't need that any communication link to work. Basically, in the good old days, it was there as to make the relay a bit faster, but not essential lah. It can still work without that link.
So meaning then the backup for the insulated cable for you know extra high voltage cable. So it's not distance lah.
I didn't understand the first part. What do you mean by insulated cable?
The normal PVC cable or SLP cable.
Let's say 33, is it?
No, extra high voltage lah.
At 132, let's say.
So it's instead of transmission cable, is an insulated SLPE cable.
Okay. You want, if it's a 132, then you will need an optical fiber which is laid separately lah.
But the optical fiber is for the differential lah, current differential.
Yes,
but what is the backup? Is it using distance protection as a
backup?
Yeah.
They still use distance, but I'll tell you, from what I know, it's not a very good backup, but you have no other choice. We'll talk about that later, Raman.
All right.
Okay. Now we come to this. This is actually meant for a pilot wire using what's called a circulating current principle, but it also applies to this current differential relay. So you imagine that it's got two coils. One is called a restraint coil, one is called an operating coil. So for the current to operate, for the relay to operate, there must be a current flowing here which is higher than this current. Effectively, that's what it means. So what happens if you have a cable? So in this case, you will need a CP here, you need a CP here, and you need a communication link between these two. So in the case of the pilot wire, we use copper wires in the good old days. But in the case of current differential, we use an optical fiber. So essentially, a current differential and a pilot wire, they work exactly the same principle. Okay, the same concept applies to both current and differential, to differential relay. They're exactly the same. So how does it work? So you imagine that there is a load or external fault current. So there'll be a current flowing here, there'll be a current flowing here. So when it comes here, where does the current flow? So you got two paths. One will flow through the operating coil, and the other will flow through the pilot wire. So you imagine that this is a very high impedance. This operating coil is very high impedance. So if the operating coil is very high impedance, then the current flowing here is very small. So where does current flow? The current then flows in this wire, this pilot wire. This pilot wire in the good old days is just a copper wire, a very small copper wire, 2.5 mm squared. So we've got a very small wire current, maybe about 20 milliamp DC, flowing through this. So what does it flow through? It flows through a restraint coil. And when the current flows through the restraint coil and no current flows through here, then you will say, hey, the relay is not supposed to operate because no operating current. So no operation under normal load condition. What happens if you have an internal fault? If you have an internal fault, there is a current. So this current comes in, what do? I got two parallel paths. One is this and one is this. And the two of them are approximately equal. So we imagine half the current flows through here, half the current flows through there. And when this happens, the operating coil current will say, hey, I'm bigger, or rather I'm equal to this, this is a stronger current, it's a stronger coil. So this coil says, I see the same current as you, I'm able to beat you, so this relay will then operate. And this relay will also operate. So for an internal fault, this relay then trips, this relay will trip this breaker, this relay trips the breaker. And if you got a second current coming in, it is even better. So that's our current differential relay, that's our pilot wire relay. So the pilot wire relay was used for many, many years. But now, as I said, they probably have stopped manufacturing because there's no demand. And anybody got any questions about the pilot wire? I don't have enough time to handle it right now. I can handle it later. So if any questions, please let me know. I'll try to find some time to answer your questions. Okay. So, and why do you call it circulating current? because the current flows in the flow circulates around here. So we call it circulating coil current. And in the good old days, we even have another word called a merge price protection. Okay, somewhere there's a word merge price. Okay, so we use different words for it, like current difference, differential, pilot wire, merge price, circulating current. They're all the same. Okay, so essentially they all work on the same principle. So in the case of the pilot wire, the two relays at the two ends must be exactly the same. Okay, and even the same ratio. In the case of the current differential, they need not be of the same ratio, but the TMB standard says they want them to be the same ratio. So technically speaking, there was a project where we told them, hey, you can have different ratios. Both TMB and power grid in Singapore, they refused. They no, because there was some CT problem. They no, we want you to make sure they're the same ratio. That's a requirement, but actually not necessary. It's a preference, in other words. Okay.
Engineer Lee.
Yep.
For the fiber optic communication, fiber link type, so the CTs are not electrically connected in a way,
yes.
right? So
not directly electrical, but only through that communication channel. So in the case of the pilot wire, there will be a current flowing here. In the case of the current difference, digital signals traveling here. That's all. So as you say, yes, electrically, there is, in the case of pilot wire, there is a small current, but this is DC, nothing to do with the AC. So this drawing is not the real drawing. In the notes here will tell you this is not the real drawing, it's a simplified drawing. In reality, the current flowing is not this AC current. Okay, at the notes here will tell you a bit more. Yes, so you're right.
The way the relay actually don't have a sensor to measure the differential, but rather it is calculating all the differential.
Yes. Yeah, it is an indirect measurement. Yeah. We don't want the CT current to flow here, for example, maybe through 10 kilometers of 132 kV cable. We don't want the current to flow through there. Because we don't want the CT current to go out onto the main road and go for 10 kilometers. So we convert this into some other representative current. That's all.
Thanks.
Okay. Any other questions? So current differential relay essentially are very, very simple. Okay. There's not much to talk about. You can see here, the current differential, they send their communication link, they send signals, digital signals, and the what they call the optical fiber can be part of the earth wire. For short lengths of cable, they are actually part of earth wire, and then they go direct. Sorry, they always use this earth wire, but it can be a direct connection. But for longer cables, then they do something else. I'm not that familiar with the longer cables. Okay, so it's optical fiber. So what is the weakness of this? The weakness of this is what happens if this fails. If this fails, this relay cannot work. Okay. In the case of pilot wire, there will be certain problems. But in the case of current differential relay, if this relay fails, it cannot work. TMB will program it so it doesn't trip for internal fault, it doesn't trip for external fault. It's just a dead duck. Okay, useless. So what do we then do? That's an interesting question. Okay, so the current differential will have two identical relays. So it must be so identical, they must have what's called the same firmware, the same programming side. Now you cannot get it. Oh, I want a current differential relay. Give me a current differential, this model enough already. I'll tell you whatever the model. They have got to give one whole string of characters to describe exactly what is the programming inside. So you cannot say I buy the latest version and use the other one's the old version. Can use or cannot. It must be exactly the same. Okay. So we have this communication link. Okay, and to make sure it works, it needs something called GPS to coordinate the timing. Because by the time the signal goes from A to B, there's a slight difference, and so they have a lot of digital things that I don't even know what they are. But without that GPS, it won't work. Okay. Then at 27500 kV, one pilot wire, one current differential relay is not enough. So remember, I told you the logic or condition. So we have two current differential relays, and they must be of completely different brands. Okay, so that's what we're going to do. And of course, the backup would be the distance. So what's the weakness of this? What happens to the current, the communication link fails? Then you got no more protection. So then what do you do? So you can program something else to take over. So we have a distance relay. The problem with this programming is there are different ways to program it. It's up to you. And quite often they change it. So what I tell you now is true today, maybe 1 year from now, they no, it's no longer true. So you can use, for example, now we're going to talk about distance relay in a while. And the distance relay typically has 3 zones. So normally, under normal condition, in the traditional way, zone 1 is instantaneous. And you can actually leave it as instantaneous, but TMB don't want. TMB will say, okay, if the current differential relay is in service, I want to disable the zone 1. So they knock it out, knock it out. Then what happens? The current differential relay fails, the communication fails. They can then program it and say, hey, now I will put in the current, activate the current zone 1 if the current differential relay fails. They can do that. Then of course there's a zone 2. The zone 2 probably is permanently in service, but the zone 1 is out of service until the communication fails. But what I said, somebody may say, hey, no, we actually have done something different nowadays. You may be right. Okay, so our distance relay is therefore the what we call the backup. Okay, and this is just an extra. I won't go into it. That current differential relays, you got to consider what's called the charging current of a transmission line. But it's more technical. Anybody interested? I just put it in, but I won't go into it. Now we come to the biggest problem. Let me see how much time have I got left. I think I got probably about 2 hours. Yeah, about 2 hours left. So now we come to the next topic are the biggest challenge. So the first one, the distance relay as a backup. So let's look at the transmission line. So this is a 132 kV transmission line. So you can see there are 3 main components. We have a main current differential, we have a distance relay as a backup, and we have an auto reclose relay here. So you can see that the current differential has only got a CT input. The distance relay, you will find later, needs a current input and a VT input. Now the main protection must have a communication link. The distance relay used to have a communication link, which is activated only under special conditions. But nowadays, TMB no longer use it. If I were doing it, I probably would put it in. Okay, and then of course, if there is a fault on the line, the possibility is that this fault is a transient fault. Transient fault means temporary fault. So we trip the breaker. The moment we trip the breaker, the fault disappears. So why don't you close back the line automatically? So we have a current differential. Sorry, a current differential relay says, hey, I detected a fault, I trip. Now I'll send a signal to initiate sorry, an auto reclose. So the auto reclose will then send a signal and close the breaker after a short time delay. So this is the basic scheme for 132. The 275 kV is the same, except we have 2 main differential relays. So we have 3 CTs, 2 CTs for main, 1 CT for main 1, 1 CT for main 2. So main 1, main 2 refer to the 2 current differential relays, and they act in parallel. They are redundant. And the other difference is that this auto reclose is a single 3-pole auto reclose, which I'll tell you about later. Okay, so this is a basic scheme for a 132 kV transmission line. So any questions? Okay, what is distance relay? So I'm going to tell you a distance relay. Number 1 is a directional relay. In other words, what we're going to do is we have a cable, a line between A to B. So we're going to put a breaker here, we're going to put a breaker here, we're going to put a CT here, we're going to put a CT there. And at each end, we're going to put a distance relay. And the distance relay is supposed to operate for faults looking into the line. So it's a directional relay that protects a fault in the forward direction of the line. Technically speaking, it doesn't provide faults towards the back. So it is called a distance relay, but I call it a electrical distance. What is electrical distance? It measures the distance from the fault, from the CT until the point of the fault. It measures it in how? By looking at the voltage and the current. So if you feed the voltage and current into this relay, and then you say, hey, calculate Z. Z is V divided by I. And then you have a Z fault. The fault is here. So I measure the impedance from this CT until this fault. And it's a forward direction. But where is the fault? I don't know whether the fault is inside the line or outside the line or at the breaker, at the bus bar. I don't know where it is. So what I do need to do is I need to list information. What is the impedance of this line? So when I measure the fault, I measure this and compare it. So what happens? Under normal condition, let's say there's a load here. So under normal condition, this relay will measure the impedance of this line, the impedance of the next line, and the impedance of the load. Very high. So no fault. Then there's a fault. So let's say the fault is here. So let's say I know this is, say, 20 ohms. And I set this relay at something, you can see somewhere, let's say for the time being at 20 ohms. So I measure this, hey, I got less than 20 ohms. That means the fault is inside the line. So I trip now. I trip for a fault in the forward direction of the line. So it's an internal fault. What happens? I measure, and this time the fault is here, and I measure 30 ohms. I know the impedance of the line is 20 ohms. The impedance I measure is 30 ohms. The relay will say, hey, it is a line fault, but it's not in my area. It belongs to the next relay. So it will not trip. So it measures the electrical impedance from the CT until the line of the fault by dividing voltage by current. That's all. But the setting is in impedance. It doesn't set the relay in voltage and current. So it measures the fault. It can be used for lines. It can be used for cables, but there's a slight problem which I'm going to tell you about. And TMB also use it for transformers because it can also measure transformer impedance. Okay, and it also has other applications in generators. In large generators, we use it as a backup protection for short circuit. We use it for loss excitation. We use it for power swings. Okay, so we have various applications, but today we will talk only about the distance relay. So any questions here before I carry on? You must understand the concept that it measures impedance, that's all. And that impedance is then compared against the line impedance. Any questions? So, as it says here, it uses VR, IR, the relay voltage and current to find the impedance ZR. And it measures not only the impedance, but the angle as well. The impedance and the angle. Okay, so if the impedance is in the fault lines in the forward direction, but the impedance is less than the line impedance, then it's an internal fault. And if it's more, it's an external fault. Internal fault trip, external fault, let somebody else take care of it. Okay, so when it comes to distance relays, we are going to have what's called characteristics. Okay, so I'm going to tell you we have 3 type characteristics. Okay, here, what are we seeing? We are seeing there's a substation A. So we have a relay here. This is the line, substation B. This is the end of the other line, substation C. So we know the impedance is from here until here. And we know the angle of this impedance. So we must either measure or calculate this impedance. So we know this. So we set our zone 1, which is a circle, which must pass through the origin. In other words, if the fault is exactly at the CT terminal, that the impedance is 0, it must be able to see it. But it must be the forward direction. It cannot be in the reverse direction. So, in other words, the relay is so sensitive, it's able to distinguish between an internal and external fault. So, if the fault is 1 millimeter inside here, it's in the forward direction. If it's 1 millimeter outside here, as far as it's concerned, the current now flows backward. So, it's a backward direction or reverse direction. So, it doesn't trip for faults in the forward direction because it's a directional relay used to measure in the forward direction. So how do we protect it? We're going to have what's called a characteristic. So this characteristic is what's called the RX plane. So when we measure, what do? We measure impedance. Impedance is divided into the real and the reactive part. So we're going to say, hey, this impedance that we measure has an R component, it has an X component. So we call it the RX plane. And what we then do is, the most basic characteristic is this circle. So this circle is called a mole characteristic. Where the word mole come from? It's actually ohm reverse. The ohm reverse you get mole. So this is called a mole characteristic. And you remember, where is the load? The load basically is a very low high power factor. So it's basically R. And the load is, of course, much higher impedance than the line impedance. So it is somewhere in this region. Very high impedance with a very small angle. Yeah. What happens to the fault? Now, a line has a very high angle impedance and a very low impedance. So we have a relay that says, hey, I have this red characteristic, which is less than 100% of the line. So if I see a load, the measured value is here. If I see a fault, where can it go? One possibility is the impedance now changes and it's inside here. So if it's inside this circle, it says, I see an internal fault in the line. It will then trip. So zone 1, the mole will trip instantaneously in the good old days. Okay, so that's the basic part. Now, for some reason, which we're going to talk a little while, there is this last part of the fault of this line, which is not covered by zone 1. Very strangely, it's covered by a zone 2. And zone 2 is slower than zone 1. We'll see why. So we have a zone 1 relay that covers less than 100%. We have a zone 2 that covers more than 100% of the line. So if a fault occurs in a line, it can either be in the first part, it will trip immediately. Or it can be the second part, it will then take a bit longer to trip. So this is also a mole characteristic. What happens if the fault is outside the line? It can be on the bus bar. It can be on the line, the next line. Do you want to trip for a bus bar fault? No, but why? I got my bus bar protection. Do you want to trip for a fault here? No, because this one has got another distance relay. So what we do, we make zone 2 slower than zone 1. So there's a fault here. This zone 1 will see it and trip immediately. This zone 2 will say, I saw the fault. Before it can trip, that zone 1 has already tripped. So what's the purpose of this zone 2? The main purpose is to protect against internal fault in the last part of the line. But it also can act as backup protection for the bus bar fault. Because there's a bus bar fault, we have a bus bar protection very fast. If that bus bar protection fails, we have a zone 2. Then what happens to the faults in the next part of the line? Same thing. We have a zone 1, which will trip faster than the zone 2. By the way, I'm talking about the traditional protection. Later on, you find that the zone 1, as I said, in TMB, has been deactivated. So that is our 2 mole characteristic. On top of that, we have a third zone. It's called offset mole. Offset mole has got a forward characteristic and a reverse characteristic, a zone reverse ridge. Typically, this is about 10 to 20% of this. And what this does is essentially act, for example, as a backup protection for the bus bar fault here. So very good, right? And this one also covers 100% of the next line. But I'll tell you from what my guess is, this relay has never operated. Why? Because it is so slow. If it ever operates, by the time it operates, probably the system would have collapsed already. And this is too slow. So it has got a forward reach, it's got a reverse reach, and it's extremely slow. So it's got zone 3. So effectively, I will not be talking about zone 3. I will only talk about zone 1 and zone 2.
Mr. Lee, I'm Kennedy here.
Kennedy, yes.
Can power swing cause zone 3 to operate?
Power swing can cause a relay to trip. That distance relay to trip. That is true. Because a power swing, I'm sure, Kennedy, you know that a power swing there's a very fast changing voltage and current. The voltage goes up, the current goes down. The voltage goes down, the current goes up. So what is changing? The impedance is changing. So under normal condition, you could have a power swing. Maybe the power swing is here. Doesn't matter. But if you have a power swing, the power swing can come inside zone 2, it can come inside zone 1. And if it goes inside zone 1 and it is activated, this relay cannot distinguish between a power swing and a internal fault. It measures impedance, so it doesn't care. So to prevent that, of course, then we have a relay called a power swing blocking relay. So you have to be careful. Yes, in the middle of a power system, you can have a power swing, and that can cause the system to break up because you have cut off. It happens right in the middle of the system. Cut off two parts of the system from each other, which happened once in around 1970 something. It happened as I remember lah. Of course, Munyo will be able to tell you better lah. But I remember that there was a problem, and it became a big thing in the paper lah. Power swing and all that. Yes, you're right. We'll talk about power swing, but only in passing later on. So, any question? So this is the mode and the offset mode. Okay, there's a third characteristic which we're going to talk about a little while. So any questions? So what are relay settings? Number one, what's our characteristic? Number two, what is the impedance setting? And number three, what is the angle? So there's an angle here. Okay. This is the second characteristic. It's called a quad characteristic. Now, what happened is, Kennedy will tell you that there are what's called high resistance faults. High resistance faults are that, if you can see this one, one of the problem is if the fault is very low impedance, resistance I'm talking about, sorry, very low, the fault is in the middle, very low resistance, the fault is somewhere here. But what happens, the fault has a very high impedance. The resistance can go outside here, and the relay cannot trip. And we had experienced this, especially when the first time we had it was when we had the distance, the 275 kV system. I'll tell you the reason later on. So we have this high resistance fault. So this distance relay is not very good at that. So it can cause the system to collapse. So, and at that time, that was the technology we had. We couldn't do anything. So we did something else instead. So nowadays, with numerical technology, we're able to come up with a quadrilateral characteristic, a four-sided characteristic. Effectively, these three are useless lah. I don't know why they even bother to do it. So the part that we're interested in this one. So you can see in this case, we have a line impedance or a relay impedance, but we can add an independent resistance. We can say, hey, I want to add a resistance of say 10 ohm, 20 ohm, 30 ohm, 40 ohms. So what have you done? Instead of the small circle, now you have a very big reach. So this is a quad characteristic that is able to take care of high resistance faults. Quad characteristic. Okay. You can see here the difference. You can see the load is here. Load is an impedance, but it's well outside. Okay. Then the quad you can see is here, and your mode or offset mode is here. So which provides you a high protection against high resistance, of course the quad lah. And we like to use it especially for the earth fault relays, because earth fault relay is where we have the high resistance. So the distance relay is protecting against short circuit and earth fault. Okay, the measured impedance is in the forward direction. Okay, and in the first quadrant. So now the measured impedance is in this quadrant. Okay, that's one that we are interested. Okay. A distance relay is a minimum of 3 zones. So the 3 zones are independent. So we have zone 1, which is supposed to be instantaneous. But I'm going to tell you in a little while, it's called underreaching. And it only covers the first 80% of the line, like what I showed you earlier. And then there's a zone 2, which is overreaching by the time delay, and it's set at 120% of the line. But it also has got some other limitations. So I'll come back to that later. And what's that? It may be the main protection for the last 20% of the line. So if you use distance relay, then the last 20% is protected by zone 2. It's not protected by zone 1. And it's also a backup protection, remember, for downstream bus bar faults. Okay. And then there's a slight delay in zone 2. Okay. And then we also can do something called carrier send, which I'll tell you in a little while. Okay. Carrier send. Okay, and zone 3 is, as I said, effectively I'm not going to talk about it. So distance relay. Now, why do we set it 80%? Why don't you set it 100%? Okay, so you can see here the circle here is always set at 100%. Why don't we set it at 100%? We can do it, right? Okay, but we're going to create a problem. We may create a problem. Why? So to understand this, we'll look at the next drawing. Okay, let's look at it. So you can see now, distance relay, we need two, one at each end. And the two relays are identical in the sense that 80%, zone 1 is 80%, zone 1 is 80%. Zone 2 is 120%, zone 2 is 120%. Zone 3, forget it. So zone 3, you can see there's a reverse reach. So we have zone 1 and zone 2. So why is zone 1 set to less than 100%? That's a big question. And the big question is very simple. The answer is very simple. The answer is we are not sure of that measurement. When you say the line is 20 ohms, how do you get the 20 ohms? I calculated it. Is there an error? Yes. Error not in the calculation, because the calculation is based upon the dimension of the tower. And you don't have one tower of towers, you have different tower of towers. So different tower of towers, they have different impedances. Okay, that's the first problem. Second problem is, okay, I measured it. Yes, in the good old days, we used to measure the line impedance. But what do you use to measure? Instruments. What errors are there in instruments? 5%, 10%. So your measurements also got errors. So in other words, whatever you do, we don't really know what is the 100% impedance is. We don't really know. We just make, we think the line is maybe 20 ohm plus minus, let's say 5%. So what happens is that exactly 100%. For example, you say, I want to set exactly at 20 ohms. You're saying, I want it to measure accurately until 19.99999 ohms, it must trip. 20.0001 is the next line, mustn't trip. No relay in the world can do it. Even if the relay can do it, the CT's got errors. So you cannot set to exactly 100%. So what must you do? You only two choices left. Either you set at more than 100%, which is called overreach, or you set it at less than 100%, which is called underreach. So you want this to trip only for internal fault. You don't want to trip for external fault. So you underreach it. So you set it at 80%. So even if the error maybe a lot of 10%, you come to say 90%, I'm still a bit clear of this. Maybe I'm going to take a risk. I'll set at 85%, 88%. But the universal rule is, don't be too clever. Let's set it at 80%. So we set it at 80%, and we say, okay, for the first 80% of the fault, you can see 80%, this relay will trip instantaneously. Then what happened to the second part? This zone 1 cannot operate. Then we put the zone 2. And by the same logic, we cannot set zone 2 to 100%. We set zone 2 at 120%. Overreach. That's where the problem, that's where it is. That's why we have this underreaching and overreaching. More than 100, less than 100%, more than 100%. Any questions here? Any questions?
Mr. Lee Chung here again.
Yeah, Chung.
Have you ever come or anybody raise this question when the line is too short? We cannot use distance.
Yes, yes. Well, not lines, cables. Cables are even worse. Why? I give an example. Between Pengerang in the rapid project to the TNB substation, if I remember, about 2 kilometers. What did they do? They put a big fat cable. What's the size of the cable? I can't remember now. It's something like 800 mm, 1000 mm. How many cables did they put? If I remember, they put in 2 cables. Ong, I think with that can confirm that because I don't remember. I think they put in 2 cables of, let's say, 800 mm squared. Because this fat cable, because 2 of them, what is the impedance? 0 point something ohms. So what happened? Impossible to set it. And that's a problem with distance relays. It doesn't, and I'll tell you in the notes later, it doesn't work very well for short lines. So you will have a problem. But you have no choice. I'll come to that later on, Chung.
Okay, thanks.
Do you remember what's the size and length of the cables?
Have to check.
You have to check. Never mind. You can share that later on in the group chat. Okay.
Okay.
So, so I think once you understand that, then you understand the problem. So what it means then, if we have this, so I'm running behind time now. So what happens? The zone 1 will never trip for external fault. Zone 2 can, the main purpose is trip for the last part of the internal fault, but it can act as backup protection for bus bar fault and the next part of the first part of the next line, only the first part. If the fault is here, then fault is say, for example, at this end, then it cannot act. So the zone 2 provides a limited backup for the next line, limited. The main purpose is to act as a backup for the bus bar protection, because this bus bar protection can fail. So, and the same thing, so in other words, if there's a fault here at the bus bar, if the bus bar protection fails, this relay cannot act as a backup quickly. It has a reverse switch, but the zone 3 is very slow. So the next relay that we'll see will be this relay and this relay. Because this relay will say, I saw a fault at the end of the line, so it will trip. This relay will say, I saw a fault at the end of the line, it also will trip. So the remote relays will trip. So the GSO guys, if you find that, hey, you got multiple relays tripping, line tripping, let's say you got this bus bar and all the bus bar, so all the lines feeding this fault is tripping, then probably it's a backup protection due to some reason. Either a fault in one of the lines somewhere, for example, the fault could be here, and this relay fail. Okay, then maybe that can happen. Okay. Zone 1, zone 2. So essentially that's
Mr. Lee, so
yeah.
if the fault at the middle of the line, so both A and B will trip lah.
Fault where again?
The middle of the line.
At the end of the line, are you referring to?
The middle of the line.
If the fault is anywhere between the line, between the two CTs, the both relays must trip.
Both right, correct.
It must, because like a current differential, because in a you have two fault currents coming in, so you must trip two sides. Okay, this is a distant relay, it will trip this side. This is a distant relay, it will trip the side. But of course, before this can happen, the current differential relay probably will trip first.
Yeah.
Okay. So in the transmission system, in the interconnected system, you must trip a minimum of 2 circuit breakers. In a generator, even worse. You got to trip not only the breaker, you got to trip the field breaker, you got to trip the turbine and so on. Okay. So I think I've covered what I want to tell you. Okay. So I think most of these points I mentioned already. I'm running a bit behind time, but you can see. So now what I told you just now, I forgot to mention, but what I told you just now is true if the distance is used as the main protection. Then what I said is true. But I say in general, zone 1 is not activated. Why? I mean, can we leave zone 1 to operate as it is? You can, but TNB and even SCB, as far as I know, SCB is solar energy, they don't activate it. So they deactivate it until the comms fail. The optical fiber fails, then they activate this. Okay. So what I said just now is true of a distance as a main protection, but in general, it is not true if it's used as a backup. So backup zone 1 it may not be in service. You got to look at each particular utility, what they want from you, in other words. So now there's a problem.
Why they disable, Mr. Lee? Any reason?
It is a philosophy, that's all.
Philosophy, okay.
I mean, I said there are different ways of putting it. Since it only trip for line fault, and a line fault, why don't you put in extra protection? It doesn't cost me anything, but they don't want, that's all. Your preference. Yeah, like a preference engineering. Okay. I got 2 very fast relay, I don't need a third. Let's say I got 132. I got 1 very fast relay, no need. I'm very confident about my current differential, no need. It create more confusion. So, your preference. If you ask me, I would do it.
Okay.
Because I would prefer that way. But another guy would look at it differently. Now, you can see we have a problem. If this is really used as a main protection for a line, why? If there's a fault in the middle, 60% is covered by zone 1. The last 20% here, one end will need a zone 2. And zone 2 is slow. 0.3 seconds, 0.45 is slow. I want to make it faster. So in the good old days, not nowadays. In the good old days, what we can do is we can send a signal from one side to the other side. We can do what's called a permissive overreach transfer trade. It's a very big word, right? Permissive overreach. So essentially, okay, I don't think I got a drawing here. Essentially, it's like this. Okay, if I see a fault here, One side will see in zone 1, but the other side sees in zone 2. This zone 2 is very slow. So what do? I can send a signal from here to here. I can say, hey, I saw a fault in zone 1. It's an internal fault lah. But my friend at the other end, I don't know whether he's in zone 1 or zone 2 lah. So never mind lah. I'll send him a signal lah. Hey, I saw a fault. So when this guy sees the fault in zone 2 and he sees the signal coming in from the other side, that he had trip on zone 1, he can then say, hey, I saw in zone 2, my friend saw in zone 1, where's the fault? Internal fault, let us trip faster than zone 2. So this was done in the good old days, but nowadays they no longer use it because, as I said, remember I told you, distance relay no longer have a communication link, but you can put in a communication link. Okay, so that's what zone 2 means lah. Okay, so we have this very big word called somewhere in the notes called permissive overreach, underreach. Sorry, permissive underreach. Why? Because zone 1 is sending the signal, and zone 1 is an underreaching relay. So it's called permissive underreach, overreach. I'm sorry, transfer trip. Okay, so it's not important nowadays because nobody uses it because the zone 1 is this used only if you have using the distance as a main protection. Okay, so you have this word permissive underreach transfer trip. Okay, so we have there are many words for it lah. Permissive underreach. Then they usually call it carrier acceleration. They also call it carrier aided. They call it teleprotection. So they all mean about the same thing. A local zone 1 will send a signal to the remote zone 2. So if both see the zone 1, both will send signal, but no use because both have trip in zone 1 already. So if they're falling on one side, so the one that's nearer see a zone 1 will send off to the zone 2 the other side. Zone 2 plus the carrier coming signal trip faster than the normal zone 2. That's what it means lah. Okay, so it's called underreach because the signal is initiated by the underreaching zone 1. Okay. This is called end fault. End fault is like this. This basically, okay, sorry, this is what I meant lah. So you can see here, where's my fault? My fault is here. So I got a zone 1 with the delayed zone 2. The other end, zone 1 with the delayed zone 2. My fault is here. So what happened? This side is in zone 1, but this side is in zone 2, which is very slow. So what they do is, this one sees the zone 1. You can see the zone 1 here. It will do a CS. CS means carrier send. It will send a signal. So to the other side. So this gets a carrier receive. So a zone 2 plus a carrier receive, let's trip faster than zone 2. That's what it means lah. So zone 2 without the carrier, zone 2 with the carrier. CR is the carrier. The next part of the fault. Okay, so to summarize, what's the difference between current diff and distance? So you can use, sorry, what's the difference between zone 1 use as distance used as a main and as a backup? So if the distance used as a main and as a backup, so if you use 21Z as a main if you don't have a current diff. Why no current diff? O-line lah, no optical fiber. Until you put in the optical fiber by replacing the overhead earth wire, you cannot have a current diff. So what do? Meantime, I'm going to use 21Z as a main protection. And this has been done for some projects overseas. So what we then do, zone 1 will cover 80% of the line. Okay, it will trip for faults in 80% of the line. And zone 2 as a backup for faults in zone 2 will cover 120% of the line. Zone 2 is as a backup for faults in the remote bus bar and the next part of the line. And we also use teleprotection. Remember the PUTT. But if you're going to use zone 1, the distance as a backup, then of course, because you got this, then I don't want to have zone 1 anymore lah. No need lah. So I only activate zone 1 only if the communication fails. That's the difference. And sometimes when they activate it, they even put a small time delay, which I don't understand why. Okay, but you can do that. So now we come to what are the problems with differential relays. Actually, differential relay got a lot of problems. Okay, but You have no choice. So how do you set it if you have long lines and short lines? Very difficult to set it. It can be impossible to set it. Okay, I'll show you the example later on. So it's not very good for, okay, I'll come back to this in a little while. Very difficult to test it. So you're going to set it at 0.1 ohms. How to test it? Very difficult to test it also. Okay. I hear that. The very difficult to set for short lengths of lines or cables due to lower limit of relay setting. Maybe you set at 0.1 ohm, but maybe the lower setting is 1 ohm. I don't really know. I'm just making a guess now. How do you set it? We may have this problem. And then we have power swings. The power swing is a change of voltage and current. And the distance relay will see the current diff doesn't care because the current changes at the two sides at the same time. So we don't care. That power swing will can cause the distance relay to trip, and it will trip during the time when you need it most, when you have an unstable condition. And then you have other problems. What happens when the VT fails? Why? The VT is supply goes to MCB. So there was a case, the MCB tripped due to some fault somewhere, a surge somewhere. The relay said, I got no voltage. No voltage means the fault is at zero. The fault is at the close up. So what happened is the relay has a feature called VT supervision that's able to detect loss of voltage due to a VT trip. Then you will block it. So we need a blocking for this VT supervision. What happens if you switch on to a fault? So in other words, you are here. Somebody earth the line by mistake, and unknowingly then switches it on. So now you got no carrier send because this relay cannot see it. So they then have a special feature that says, hey, if I close the breaker and immediately within say less than 300 milliseconds I see a fault, I must be closing on to an earth. It will then trip it immediately. So we have a special feature called switch on to fault, SOTF. SOTF, okay, to expedite fault clearance of zone 2 fault when energizing a line with a remote end fault. Okay, then we need this power swing blocking. You can see distant relays have a lot of problems. This one I won't go into. These are very technical. So what's the difference between 21Z and 87? So distance can be used as a main and as a backup, or only as a backup. So it's very versatile in that sense. Okay, but a current diff only can use as a main, no backup. Current diff is always instantaneous, whereas the distance can be instantaneous, can be time delay. Okay, and what are the inputs? Current diff, only current. Distance needs voltage and current. CT ratio, the two CT ratio can be different. And by the case of current diff, they must be exactly the same. In the case of TNB or utilities. Relay models can be different. This one, the relay models must be exactly the same, must be identical. Communication is not vital to a distance relay. It can operate if there's no communication. Current differential cannot operate if there's no what we call communication link. What about failure? So failure of communication, distance relay can work, current diff cannot work. Relay characteristic, current distance got 3 type characteristic. Current differential relay, we have a characteristic, we just call it the bias characteristic. Settings, the setting of a distance relay has got 3 settings. What's our characteristic? What is the impedance? What's the angle? Whereas the current diff, very simple. What's the pickup current? What's the bias slope? Load encroachment, can it trip during a fault, during a heavy load? Current diff cannot, because the two currents are the same, whereas distance relay can. Stability test. So stability test is to make sure that relay polarity is correct, and for current diff we need that. Distance we don't need that. Okay, so now we come to limitations of what do you call distance relay settings. So
Kennedy here.
Sorry, come again.
Kennedy here. The last slide you mentioned that it can trip due to heavy load.
Yes.
High load.
Yeah.
How high normally?
You have to do your calculation. You have to go and check So in other words, you have to convert everything to impedances. So you have to go to this. The formulas are very standard formulas. Yeah, they are easily available all over the place. Essentially, you have to take this this MVA. You know the voltage. You know the MVA. You can convert it to an impedance. And similarly, this is an impedance. So you find out whether there is this impedance inside this circle, that's all, or this characteristic. So it's a very simple calculation. Any relay guy should know how to do it. It's in the manuals anyway.
Okay.
Okay.
Thank you.
But so far, I've never heard of a case that happened unless you got extremely long lines, which I'm not aware of. Not in Malaysia anyway. Okay. Now we come to a problem of distance relay. This guy's a bit technical, but I won't go into detail, but I'll just show you this. You can see I got let's say I won't call it a long line, a medium length of line, and then you got a short length, or maybe and then another medium length. So let's go and put impedances. Let's say this is 50 ohms, this is 40 ohms. We're talking about zone 2. So how do you set this? I'm going to say that zone 1 at 80%, so 50 ohms, 40 ohms, that's okay. Zone 1 not a problem. Zone 2, I'm going to set at 120%, which is 60 ohms. Right? So I'm going to put at 60 ohms. What happens? The next line is a very short line. It's only 10 ohms. So if I put at 60 ohms, I've gone to 100% on the next line. And that means that this zone 2 and this zone 2 will overlap, because this one will cover only 80%. So there's a problem. So to get out of this problem, either I reduce my zone 2 reach to 55 ohms given here, or I increase the timing. So you can see I have a very difficult to set it when we have this what we call long lines followed by short lines. Very difficult to set it. Okay. And then there's another problem with transformers, but that's a bit more technical, so I'll leave it out in case anybody asks questions. The last part talks about directional faults. Directional faults was something that we saw when we first energized transmission system at 275 kV voltage. And I remember I was in Ipoh, and the second line we energized was between Papan to Temenggong. Okay.
Really?
And was there a question?
Yeah. Sorry. There's a question from Agong on the distance relay. Are you moving from distance relay?
Yeah, you can ask.
Yeah. So he's asking, in case of large solar farm, short circuit current from LSS is about 1.5 times LSS capacity. Will distance relay face a problem with such low fault current from LSS?
Technically, okay, I know what you mean. In other words, what happens with solar farms, wind turbines, solar, anything, these are low energy, low power sources. And with the inverter, the maximum current that you get is probably around 1.2 to 1.5 times. So in other words, I got, let's say I can produce 1000 amps, I view in amps. The maximum short circuit current is about typically around 1002 only, if you ask me to guess. So 1002 means that it is not a very high fault current compared to the load. Load is 1000, fault current only 1002. Will the distance relay work? And the distance relay doesn't care, because distance relay only measures voltage and current. So voltage and current converts into impedance. So as long as the impedance is less than the value, it should work. But of course, there will be a minimum of current that say, hey, below the minimum current, I cannot work anymore. Say like current differential, the minimum will be 0.2 or 20%. So a distance relay also got a minimum. If you ask me to guess, I would say around 10-20%. So I don't think there will be a problem. Agong, have you come across anybody that says that there is a problem due to the low current infeed from solar farms? Agong, do you have any experience?
Yeah, so far no, never heard.
So far as I know. Okay, then we come to this directional fault. So directional fault, I say if I go back to history, I remember that when I was in Ipoh, and the second line we energized was from Papan to Temenggong, and for some reason we have faults, the relay didn't trip. We had two distance relays, but they both didn't trip. They were 275 kV. And later on, we found that it was due to bare vegetation. But either it's burning vegetation or it's bamboo, very fast growing bamboo. What TNB does is they patrol the line, I think, don't know, once every 2 weeks. I don't know exact, but every few weeks they will patrol the line and they'll look at what's called danger trees. This tree is dangerous. They'll mark it, and then there'll be a follow-up gang that says, okay, let's go cut down the tree. The problem with bamboo, they grow so fast. One moment is not there, a couple of weeks later, it's gone so high. And during wind or windy weather or strong wind, maybe it comes very near to the line and it causes a flashover. It's a high resistance fault, and the relays were not able to trip. So what did we do? We then, at that time, the technology, we didn't have this current diff. So what did we do? We then come up with this directional relay. So a directional relay is completely different. It is not a differential relay. It is not a distance relay. It is just a permissive tripping relay. In other words, what does directional relay do? The symbol for directional relay is 67N, and it's got direction. So every line has two directional relays that are looking towards each other. So what happens in a fault? If there's a fault, if the relay sees a current in the forward direction, it will send the signal. You can see the CS, it will send a signal. So if the fault is here, you can see the fault is here. So three relays see the current passes through three relays, but only two relays will pick up. So this relay will pick up, this relay will pick up, it will send a signal from here to here, here to here. Similarly, on the other side, two relays will pick up. So what's the condition to trip? The relay must pick up, it must get a carrier signal, then it will trip. So this side, pick up, but no receive, won't trip. This side receive, but no pick up, won't trip. So these two relays are the only two relays that trip, so we call it a directional earth fault relay. And for that to happen, it must have a carrier, it must have a channel, communication channel. So it's just it's basically an earth fault relay, a directional fault relay with a communication channel, very different from current date, very different from what we call the distance. Okay, but from what I know, Kennedy can confirm it. This relay is now basically useless. From what I know, for the last 10 years, 20 years, it has never tripped. Am I right, Kennedy? Do you remember whether this relay ever tripped? Last 10.
No, directional.
Directional fault.
I'm not so sure.
Okay, because why? Because now we got a current diff, and the current diff has a setting of only 20%, and 20% means the fault current is very small, so it's able to detect high resistance, low fault current. So effectively, I just include it for completeness, but it is of no interest, lah. Okay. So, any questions? Now I want to do a test. This test is not, if we do it together, lah. Why don't you do it? So that it's like a revision. Instead of giving you as a point A, do you remember this? Do you remember that? So instead of that, let's do a test together. Now I will ask the question, and anybody can say, hey, I'll give you the answers. Okay. So it's up to you to give the answer. And of course, give a wrong answer, right answer, doesn't matter, lah. We just for the fun of doing it as a method of reinforcing the learning. Okay. So which is the unit protection? Current date, distance, or both of them? Anybody want to answer this question? Agong, you want to start, since you I think you're quite knowledgeable. Agong, you want to start?
Yeah, current differential lah.
Current differential is the only main protection.
Yeah.
It's a unit protection. Okay, thank you, Karen. Which relay has both voltage and current inputs? Wing, you want to try this? Which relay has both voltage and current inputs?
Distance
relay.
Only the distance relay. Okay. Now, how many current differential relays are provided at each line at each 275 kV substation? 275 kV substation. How many current differential relays we need at each end? For each line, in other words, like each end.
Two.
Anybody want to guess?
Two, main and backup.
Thank you. No. That's it. It's not main and backup. It's called main 1, main 2.
Yeah, main 1, main 2. Yes, sir. Sorry.
No, it's not called main and backup. It's main 1, main 2. So main backup will mean it's a bit slower. Both are equally fast.
Yes, sir.
So
Main 1 and main 2 of different make.
Yes. Thank you very much, Adashi. main 1, main 2 of different makes, but they operate at the same time. Remember, it's a OR logic. Okay, it's a distance relay, a directional protection. Anybody want to guess this? Is a distance a directional protection?
Yes.
Thank you, Adashi. Okay, what is a typical zone 2 setting? Hafiza, you want to try this? What is a typical zone 2 setting of a distance relay? More than, equal to, less than the line impedance? Hafiza, you want to answer this? Are you online, Hafiza? Okay, anybody else want to try this?
More than.
The answer is more than 120% typically. Okay, zone 2 is typically set at 120% of the line impedance is an overreaching protection. Assuming that zone 1 is deactivated, can zone 2 operate for a zone 1 fault? So it's a very basic question. So like in the case of the distance relay for a transmission line, very often we deactivate zone 1. Can zone 2 operate for zone 1 fault in that case? Yes or no?
Yes.
Yes.
The answer is yes. Why? Because zone 1 is inside zone 2. So zone 2 has a higher impedance, so zone 1 must be inside zone 2. So yes, of course it can operate. Just a trick question. Now, which equipment are well protected by the zone 2? Well protected means it's 100% protected by the zone 2 protection. Is it an internal line fault? Is it an external line fault? Is it a downstream bus bar fault? Is it an upstream or reverse bus bar fault? So in this case, there should be 2 answers. Which equipment are well protected by the zone 2? 100% protected, okay, by the zone 2 protection. So which are the 2 answers we're looking for? Anybody want to guess?
Internal and downstream.
Internal line fault. What's the other one?
Downstream.
Downstream bus bar fault. So you will see a fault at the end of the line, but the bus bar fault that's behind it is not protected by zone 2 because zone 2 is a forward reaching. So the reverse bus bar fault upstream the reverse, so it doesn't flip. So the answer is okay. Is the internal line fault and sorry, too clever. Internal line fault and downstream bus bar fault. Okay, where am I now? Okay. Sorry. Yeah. Where is my? Yeah. Okay. What are the basic settings for a distance relay? Is it voltage? Is it current? Is it power? Is it impedance? Is it angle? Is it characteristic? There's more than one answer. So, Hafiza, you want to try this question again as well?
Angle?
Oh, we got a new answer.
I'll try.
Okay, read that, please.
Impedance, current, impedance, angle, and characteristic.
Thank you, Hafiza. There are 3 answers. The impedance, because you need to set the what do you call how what is 120% or 80%. The angle depends upon the line impedance and what's our characteristic. And nowadays the most common characteristic is the what do you think is the most common characteristic? Is the quad characteristic. Okay.
It's quad, okay.
Okay, which of the following protection requires a communication link for its operation? So I won't tell you how many answers. You have to tell me. Current diff, distance, directional earth fault. So is it more than one answer, first of all? So anybody want to guess? Want to try? Sean B, you want to try?
I think it's 2. Current differential and directional earth fault.
Thank you very much. Who is that, by the way?
Albert.
Oh, Albert. Hey, Albert. Okay, thank you, Albert. Very good. Albert is correct. Current diff and directional fault. We need communication. Distance communication is not essential. The overcurrent relay is widely used as a backup protection. This is a trick question. The overcurrent relay is widely used as a backup protection in transmission system. Very simple. True or false? Is it true or is it false? We use overcurrent relay extensively in transmission system as a backup protection. Liao, CK Liao, you want to try this? No? Chung, I'm sure Chung, you can answer that.
It's false.
And the answer is false. We don't use overcurrent as a backup. Chung is right. It is used only for transformer, HV side, and LV side, of course. So it's not widely used. So, okay, any questions? Oh, I'm running behind time already. Any question?
There's a question from Tang JH for the Tang JH. For the 67N.
Tang from SDT.
For the 67N, do we need to do grading between each relay, time grading?
No. Okay. Tang asked this question about 67N. Because they can, if this relays can, do I need to have what they call time grading? No, because they can only trip when the fault is here. Only these two relays can trip. These two relays cannot trip. Fault is here. Only these two relays. So any you can trip for internal fault. So we don't need to have time grading. But there are some other complications which I won't go into now. The answer is all the relays have the same setting. They have the same current setting. They have the same time delay. Hope that answers the question, Tang. Any other questions?
Lee, can you repeat the answer for the last number 3 question?
Can I repeat what?
The answer for the last third
question. You're talking about this question?
Does the directional earth relay operate on principle as current differential? What is the answer? I missed that.
Sorry. Which does a what?
Yeah, the last third question.
This last question, what kind of relay?
Last third. That means this one.
This one. Does a directional earth relay operate on the principle? Oh, sorry. I missed the question. Sorry, you're right. Okay. Does a directional earth relay operate on the same principle? Oh, they say the word same. Sorry. On the same principle as a current differential or distance relay. So does it operate on the same principle as a directional differential, distance, or is it neither? So since you asked, what do you think?
Neither.
The answer is neither. Because it's completely different. It's actually a directional earth fault relay, and it is a communication channel, so it's different in that sense. And there's no relay. It has no impedance setting. Okay, so it's completely different. Yes, you are right. The answer is neither.
Thank you.
Thank you. Okay. I hope you enjoyed the questions because this is like I said, a chance for, because somehow when you take part in the question, somehow I think you learn better. And I'm going to repeat some of these questions later on during the quiz. But I don't know whether I got enough time to run it today or not. Okay, any other questions?
Mr. Lee, I have a question here.
Yep, Ling, Chung, sorry.
Yeah. During first energize the substation, or they call it commission the substation, normally they will set the zone 2 distance to instant. Any reason they do that?
I've never heard. You're obviously talking about in the case Achung is from Kimanis power station. He operates a power station by that power station exports power to 275 kV system. Or 275, Achung? Yeah. Okay. His question is, when you energize the 275 kV line for the first time, you what they did was they expedite the relay tripping for the zone 2. That's what you're saying, right?
Yeah.
I don't think there's any special reason except that just in case the current did fail, maybe I want to have a faster protection. I've never heard of that, but you can obviously can do it. For example, in the good old days, as I said, we don't have current date. When we just energize a line, I don't remember that my zone 2 must be now set to instantaneous. I don't remember. But if you ask me, I would just say, okay, just in case something happens, I got to, because last part of the fault, in case there's a fault, At least my zone 2 is faster lah. But it's really a zone 2 fault, and it happens immediately after energizing. Your SOTF, your switch on the fault should be fast enough lah. But you can do it, obviously, no harm in doing it.
Okay, thank you.
Other questions? Now we come to this. So this one can be difficult. So let's try it lah. So obviously you know that the busbar protection is very important, and busbar is very important, and therefore you need a very good protection. And the good protection must trip the minimum part of the fault, but without tripping wrongly. Those are the two requirements. So we call it security and reliability. And to achieve this, what we then do is we divide the bus bar into 2 or more zones, each with its own discriminating relay. So we're going to use the word discriminating relay, and another thing called a check relay, an overall check relay. Okay, and the result is a very complicated wiring, especially if you have a double bus bar, which I will just show you very quickly. And then the tripping circuit also becomes very complicated. If you have a single bus bar, not so bad, but double bus are very complicated. And of course, traditionally we have used a high impedance relay, but nowadays we use what's called a low impedance relay, which is very, very expensive. We're talking about maybe 10 times the cost, but of course there are a lot of advantages. And the TNB system and even SCB, they have this requirement. The 120 kV bus bar, only one scheme, only one relay required, and that must be a low impedance. And that works on a 2 out of 2 tripping, which I've told you about, the logic and condition. All about for EHV. So EHV, the choices are you have 2 low impedance, as I said, the low impedance is very expensive, or a combination of a low and a high impedance. And then duplicate. So you have duplicated the protection. So we have duplicate 2 out of 2 protection. So it's very expensive, So, but that's what we are doing for the utilities. So you can see what happens if you got a bus bar fault. In the good old days, if you got a bus bar fault, in the 1130 kV system, all you have is an overcurrent fault relay. Overcurrent fault relay, as I 3311 kV, we don't have bus bar protection. It's too expensive, so we don't do it. So we just overcurrent fault relay. Any fault, this relay was very slow, but never mind lah. What to do? I want to save money, so I go for cheap protection, very slow, but never mind. Whereas in the case of bus bar protection, in the case of this, for a bus bar protection or transmission, that's not acceptable. So what we then do is we got 4 circuits, one circuit coming in, 3 circuits going out. So for every one of them, we put a CT, and we add up these CTs. And it's basically a differential relay with 4 legs lah. Normally differential relay got 2 legs, right? HV side, LV side, transformer. But this one has got 4 CTs, and this CT is then able to detect a fault anywhere inside here. So how does it work? Okay, so how it works is very simple. So in this case, you can see we have 4 relays, we have 4 CTs. So under normal condition, you got current flowing in, Kirchhoff law says current flowing out, they're equal. So you add up all the currents in and out, must be 0. Why? It's a low condition external fault. Whereas if it's internal fault, then the currents come in, add up, then you got internal fault, the relay trip. So very simple. So that's a basic concept. Okay. So the bus bar protection for transmission substation is shown on the next slide, will consist of this. So let's look at the next slide. So this is the simplest bus bar protection that we can have. And we can have it, for example, for the H system, the H arrangement. So H arrangement, you have 1 circuit coming in. Again, in this case, 1 circuit coming in, 1 circuit going to a transformer, 1 bus section. So you can see there's a 5 circuits. So what you want to do? You want to protect the bus bar. How bus bar protection you want to give? In general, we always will give the relay in such a way that if there's a fault here on section 1, we trip these 3 breakers. Fault in section 1, trip the 3 breakers, these 3 breakers can carry on, or these 2 breakers carry on to supply load to help the system. And the fault is here, we trip these 3 breakers. So we have essentially what we need is therefore 2 zones of bus bar protection. We have 1 bus bar protection for this zone, so we call it a discriminating zone. And we have another protection for this zone, call it another discriminating zone. So we have 2 bus bar protection relays. Then the next question is, what happens if the relay trips wrongly? Then I lost my bus bar, half my bus bar. Is that acceptable? No lah, no lah. I don't want to trip wrongly lah. So what do? I put in something else called check. So I put in another. So you can see here, this is called the R1. It's your relay 1, discriminating zone 1. R2 is a discriminating zone 2. We'll come back to that. So as you can see that when this relay trips, essentially it will go and trip this breaker, this breaker, this breaker. It will trip all 3 breakers. And similarly the other side. So now I'm depending upon this relay. And if this relay trips wrongly, I have a problem. So how to make sure there really is a fault? I'm going to put in a third relay called a check relay. And this check relay will detect faults anywhere inside here. So if we detect the fault anywhere inside here, you will then say, I saw a fault. You saw a fault. The fault must be here. Let's trip this. The other says, I didn't see a fault. Let's not trip. So we have put in a check relay, another relay called check relay. So now we know we have 3 relays, 2 discriminating relays, 1 check relay. So how does it work? And now we come to a problem. There is a bus section. So I want my zone 1 to cover, if possible, only this one. But remember the problem about city location. So I cannot put my cities here, I put my cities here. So this relay R1 is fed by this city, this city, this city. A, B, and C. So they add up these 3 currents to go into here. Zone 1 or relay 1. Similarly, this relay D, E, F goes to relay 2. And what about the check? The check zone has an independent CT, which is all the 4 CTs added together. So another discriminating zone has 3 CTs. The check zone has 4 CTs. So like that, how to explain it? So how to explain it is, let's simplify it. Let's go and open this bus section first. Let's make our job easier. Let's open the bus section. And let's have a fault here. So what do you want to trip? You want to trip the left side. You don't want to trip the right side. So how does the current flow? You can see there will be a current coming in. Let's say one line carries the fault, like the other one, the feeder, a transformer, so no fault. So current comes in. So this relay will see, this CT will see a current, these 2 CTs no current. So this CT will energize this relay. That's relay A operating R1. Then relay G, a CTG, will then see a current and it will energize R3. So R3 and R1 will operate. What about R2? No current. It won't operate. So what happens when R3 and R1 operate? You can see the trip circuit comes from here, goes through R3, contact, goes through R1 contact. Now it trips the 3 breakers. You can see trip breaker 1, 2, and 3. We'll switch off the left side of the bus bar without switching off the right. And we have independent confirmation. We have different set of CTs, we have different relays confirming there is a fault. So we have a discriminating zone relay and a check zone relay. So 2 relays trip. Now we know the fault is here. Somewhere here we trip. Okay, any questions?
Mr. Lee, will you be showing also double bus?
Double bus, the concept is the same, but unless you have some special questions,
okay,
we can talk about it later.
The issue,
there's another drawing, but I don't intend to go into it, but let's see what happens.
All right, the question is, say this.
Never mind, hold on for a while, when we reach the drawing. Okay, so this is, just hold on. So, okay, so this is a very simple system, but there's one complication. What happens if the fault is here? Now, this side belongs to the left bus section 1, this side belongs to section 2. But I cannot put this CT here. If I put this CT here, then this CT is not, this one is outside our zone. So I have to put the CT here. So you can see that there is this zone, it's called an overlapping zone. This, as far as protection is concerned, is part of zone 1, is part of zone 2. The same problem that we talked about earlier on, about the overlapping, about the fault. Where is the CT location? So what happens? The fault is here. We have a problem. So let us now go and put a fault here. So instead of fault here, let's put it here. And let's imagine the breaker is still open. This breaker is open. So what happens? There's a fault current coming this way. Now you pass through three CTs. And this CT will go and operate this relay. So we have a fault. Even though there's no current coming from section 2, this will tell the relay, hey, I see a fault, you better trip. Why? Because the fault is here. The fault is here, then this one will give a current passing through 3 CTs. So this one will now trip. So this is the problem with this overlapping zone. Any questions here?
Even if the breaker is open,
Exactly.
Yeah,
Who's
because
that, by
last
the
time
way,
we had CT failure.
Wait. One at a time. Who is that, by the way?
Kennedy here, Mr. Lee.
Oh, Kennedy. Okay, wait. Thank you, Kennedy. Because we didn't recognize your voice, Kennedy. Okay.
Okay.
Okay, I'll come to the. So what Kennedy says is correct. Even if the breaker is open, even though there's no current coming from the right hand side, this one will say, hey, I see it as an internal fault on the right hand side because of this overlapping zone, which we cannot help. Because if we don't allow this, then we say, hey, I will trip only up to here, this will trip only up to here, then this one, no busbar protection. So it's either too much or too little. So we have no choice.
Mr. Lee, we had an issue last time. The CT failed. The CT exploded. It's not like exactly like what you showed, the DCT, and then both the busbar tripped.
It is possible that, okay, I come to that later. I'm not too sure what happened in your case. Never mind, I'll come to that later. Okay.
So then now they practice opening the breaker. So that means it won't help, is it?
Come again.
Hmm?
Come again. Sorry, what's your last statement?
Now the practice is to keep the breaker open. If the
okay. But it will not help because it will still flip. It doesn't matter whether it's open or closed because unless Kennedy, I'll tell you, unless it's 100% low impedance, there is a way to help, which is in the notes. I'll tell you. I didn't intend to go through it, but since you said it, I will tell you how.
All right.
Okay. So we have not even talked about the breaker closed. So what happens if the breaker is closed and now the fault is here? So what will happen? Now there will be a current flowing through this, current flowing through here, to CTJ, CTE, and CTD. CTC, sorry. But just now the fault until here. Now C, E, and F will see the fault. Will it trip or not? What happens is, of course, this one will, the J will, of course, will trip the artery, which will be 1. But what happens to E? Now, E and F, E and D are arranged in such a way the two CTs cancel each other out. Now the current flows through here and come out through here. So this is going into the bus zone, this is going out. So these two CTs cancel each other out. So this relay does not operate. Even though the bus section is open, is closed, and there is a current flowing through C and F, it sees an external fault. So it will not trip. So that's how because of the polarity, arranged in such a way that D and E will not operate for a fault here, even when the bus section is closed. So that's the difficult part, whether you understand this or not. So any questions? So I repeat that if you consider the bus section is open, the fault is here, you're going to need 2 currents through the 2 CTs. This will trip this. If the fault is here, with the bus section closed and open, there'll be 3 currents. And this will now trip this, even though the fault is on the wrong side of the bus. But what happens if the fault is here and the bus section is closed? Now there'll be a current flowing through here, and although these two CTs see the current D and E, but the two CTs cancel each other out, so this relay will not trip. So, any questions? Wayne, any questions from the floor? No?
Mr. Lee, is there a conclusion that if the fault is inside the overlap zone, you trip everything?
Yes.
Regardless you open or close the bus section.
Yes, that is true. Unless you use, there's a possibility of using what's called low impedance. If the whole protection is low impedance, there's a possibility to program the low impedance in such a way that this does not happen. But whether TNB uses it, I'm told that it's not been done. That's what I'm told, but I'm not sure. But we'll come to that later, Chung.
Okay, thanks.
Okay. So all these, I won't go into detail, but all these are described here.
Mr. Lee, Pang here from PNP. Just want to check with you, if the check zone detects a fault but not R1 and R2, what will happen then?
Nothing. If one relay trip, then it's a false. It's a false. If it's one relay trip, either it's a false tripping or the other relay has failed. So now what's sorry, who is that, by the way?
Pang from Power.
Oh, Pang. Oh, CP, is it?
Yes, yes.
Okay. So CP, Pang asked this question. What happens if one relay trip? Nothing happens because it's a 2 out of 2. So if one relay trip, either this relay trip wrongly or the other relay failed to trip. So in other words, there are two possibilities. There really is a fault, this relay failed. Or there's no fault and this relay trip wrongly. So nothing happens. So if it's really a fault, then you have to depend upon the backup, which in this case will be the distance relay at the next substation.
Okay.
Okay, thanks, Pang. Any other questions? All these are, you go through the notes, it will tell you all the details. So these are all also the same thing. Okay. Now, what the requirement for bus bar protection? So the number of discriminating zones required are as follows. Okay, maybe I show you the last drawing and then I come back. Okay, I show you this drawing. So to make it a bit more complicated, Kennedy's question, what happens if you got a bus, you got a double bus? So if you got a double bus, how many sections are there? How many zones are there? Just now was the H arrangement, we need 2 sections. So how many sections are there in this case? Kennedy, how many sections do we need? How many zones do we need? Discriminating zones.
3 here because they have bus section also. Like here got 3.
3. Why? There'll be 1 for this side. For the main bus, this is called the main bus usually. So there'll be 1 zone for here. There's another zone for here, which I'll show you later on another drawing. Okay, sorry, the second one should be up to here. Sorry, up to here. And then the third zone starting from here until here. So we need 3 discriminating zones and 1 check zone. So that's what it means here. So we have 1 check zone. We have 2 overlapping zones because there's an overlap here. There's an overlap here. So 2 overlapping zones. And we have 3 discriminating zones. I just went through. And we need 4 relays. 3 discriminating plus 1 check. So that is what we need to do. But we have a problem. Where are our cities? Our cities are located here. Where am I going to connect this circuit? I can connect the circuit to either the main bus or the reserve bus. So how do I switch? Because the 2 relays are different. So how do I switch from main to reserve? That's where the problem is. Especially if you use a high impedance. So we'll try to answer Kennedy's question in a little while. So, thank you. So, is there a question? So the number of discriminating zones required are as follows. Single bus, in this case, with a bus section, as shown in the previous drawing, we need 2 zones. So a double bus with a bus coupler, then sorry, a bus coupler, then we need 2 zones. So there are double bus, technically speaking, without a bus section. But if you have a double bus with a bus coupler and a bus section, then we need 3 zones. That's one I just showed to you. So there is a complication if you have double bus and you have a high impedance. Why? Because the number one, the bus side, the bus sides are okay, but the other circuits have got to be switched. As I told you just now, if I am connected to the main, if this CT here, the CT is here, I'm connected to the main, I must switch my CT to the main. And if I'm connected to the reserve, I must switch to the reserve. So how do I do the switching? So in the good old days, okay, we used to have, and we still have, we have what we call auxiliary circuits, auxiliary contacts, that were somehow able to say, hey, I'm connected to the main, switch all the CT circuits to the main. I'm connected to the reserve, switch all to the reserve. So we have a very complicated protection. If you look at the drawing, if you don't know what I'm looking for, you get a big headache, okay, which I didn't show you, okay. So there's the need to switch the discriminating zone from one zone to the other zone, okay. And then what about tripping? The same thing. Hey, this relays on the main, my reserve trip, so I don't want to trip that breaker. So both the CT circuits and the tripping circuit need to use this auxiliary contact, and it's a very messy drawing, very difficult to test it, okay. So that's where the problem is, okay. So how do we do this? Okay, let's see how do we do it. So you can see here, okay, maybe Kennedy got his question here. So you can see here, how many relays do I have? You can see here, there's a main bus, there's a reserve bus, and the main bus, wait, let me see here. Wait, I need, hey, how come? Wait. You can see this auxiliary contact. Okay, sorry, these are showing. Okay, these are only showing you the discriminating zone. They don't show you. The check zone is here. The check zone, no need. You can see the check zone, no need to do switching because check zone is permanently in. But you can see this one can be connected to the main bus or the reserve bus. So the CT comes here and say, hey, am I on main or reserve? Oh, I'm on main. So it will go to this contact, go to the main. Oh, I'm on reserve. This contact will open, then this contact will close, then you go to the reserve. And then there's another problem. What happens when both are closed under special conditions? That's another headache. So we have all these problems. So we need all these switching contacts. And this also applies to the tripping circuit. Because when you trip, you don't want to trip the breaker that is connected to the wrong to the other bus. Okay. So Kennedy, you got a question?
Yeah, I understand. That means just now you mentioned that this contacts are taken from the 1 and 2, 3 and 4, right? Exactly.
Yes. So these are called auxiliary contacts. Auxiliary contact means that these are, for example, are normally open contact. When these are open, when the disconnector one is open, these contacts are open. Disconnector one closes, this contact closes. So then it will switch. I'm close onto the main. So the circuit comes here and says, I will switch on to the main bus relay.
Okay, thanks. Clear, very clear.
And then the tripping circuit, the same thing. So if you're on the main, then the tripping circuit will say, this relay trip, I have to check. There's another contact for the main. Oh, the main is contact is closed. I will trip this breaker. The reserve contact is closed. Main contact open. I won't trip it. So that's what it means. All
right.
Okay.
Thank you, Mr. Lee. Very clear.
Thank you. So this is another drawing. Maybe this drawing is a simplified version of the drawing. That drawing got a lot of detail and less detail, but essentially they're showing the same thing. So can you see the same thing? This one comes either go to A or B. So it goes to A. So where is A? A is on the reserve bus R. B is on the main bus. So main M. Essentially the same thing. Okay. So then there's another problem now. hey, I do all this switching of these CTs. What happens if the contact is open circuit? If the contact is open circuit, that means the current cannot flow. There'll be unbalance. And this unbalance can cause a problem. So for high impedance relay, what they then do is they have got something called a supervising relay. So if there's an unbalance, so let's say the current, let's say the relay is set at 10%, say 30%, and there's a 10% unbalance, the current will come here. So you go through this, and then there'll be a voltage here. So this voltage goes into this relay. The relay says, hey, I see a voltage that is beyond my setting. Something is wrong. What does this relay do? 95, supervision relay. You can see this? It will switch off. It will short the protection. And switch off this protection, which means there's no more busbar protection. This is called a high impedance relay with the supervised with a CT supervision circuit. So it is a time delay So this is a time. Otherwise, before the relay can trip, you can switch it off. So it's a voltage operated time delay. That's what it means. Okay, so what they call supervision relay, CT supervision relay. And then we come to this high and low impedance. Now, in general,
regarding the CT supervision, earlier when you're starting slide, you mentioned there are 3 reasons where the CT supervision will activate. I think one of the introduction slide, if I'm not mistaken.
You go on. I didn't catch your question. Am I? You go on first. I just see.
Earlier, I think you mentioned that there will be 3 reasons why the CT supervision can operate.
Okay. I didn't go through the notes with you. Okay.
Earlier, so one of it, just now you said that. What are the other 2? No, that was actually very early of your slide. One of the.
Okay, never mind. Tell me. Because I don't remember which one. So tell me what it says. Do you know what it says?
Wait, I forgot to take note. I'll just check for you. Trip supply, trip coil, not open circuit.
Oh no.
Trip circuit.
That is trip circuit supervision. That is different.
Oh.
That is a DC trip circuit. No, this is AC current circuit.
Oh, this is for the CT.
This is for the CT. That is for the trip circuit. Trip circuit meaning that the trip coil, the DC coil.
Oh, okay.
If you want later, I can put it in. I didn't want to go into it, but since you are interested, because I'm going to issue a second revision to include the second set of notes, I'll put in a circuit to explain that a little bit, since you're interested. So they are different. One is CT supervision, the other one is DC, the trip circuit supervision.
Okay. So this one is just monitoring the CT, whether.
Yeah. So in other words, what happens is if there is a fault, there will be a current coming here, and this will be energized. But before it can time out, the relay would have tripped already. So it's a time delay voltage operated relay. So although it's supposed to measure the current, that is because this is a high impedance. So the current doesn't pass through here, it's a voltage that it measures. Okay. Any other questions? I got 2 other guys from GSO, Hira and Razlan. So ada soalan tak dari you orang, Hira and Razlan? Any question from you all? Now we come to something new called low impedance. So low impedance, the big advantage is very flexible, and low impedance relay, one of the big advantages is we don't need all this. Basically, the CT goes direct to the relay, and then, okay, I'll show you how they do it. To be honest, I'm not familiar with that wiring. Maybe people like Frederick are. You can see it. So the CT goes direct to the relay, but they also wire the status of this. So they go inside there, and the switching is done inside the relay. Oh, this CT is on main. I'll connect it to the main. Or this CT is on reserve. I'll connect it to the reserve. All done by soft switching. So all these are done by the low impedance relay. So now it's a very intelligent relay, but very expensive. Okay, and it avoids all this problem about having to do all this switching. Okay, So that's called low impedance relay. And I will not go into too much detail about low impedance, but there are a lot of differences between low impedance and high impedance relays. But the main difference in this case, it is very, very expensive. My guess, as I say, is probably about 10 times more. I already talked to you about the line CTs and busbar side CTs, but now we come to a very interesting problem. We're talking about busbar protection now. Now, if the fault is here, remember we say it's part of the busbar protection. But let's take a very interesting case. What happens if this breaker is okay? I imagine this case now. Let's imagine you have a 275 kV substation, and let's imagine you have remember you got two busbar protection on 275 kV, and both are low impedance. What can you do? Now, let's take this case. There are two cases of interest. Let's take this case that this is open. The busbar is energized, but this is open. And then there's a fault here. But nobody knew there's a fault. This line, in other words, this line is not energized. The line is not energized, there's a fault here. And then you switch on the fault, switch on the load, switch on the line, switch on the line. So what happened? It comes here, it will say there's a busbar fault because the busbar protection starts here. And it will trip off the whole busbar, even though the fault is not on the busbar. But it will not trip the line. That's what we did, right? Because we have no choice. Like this is remember, an overprotection and an underprotection, a blind spot. But what happens if you have a low impedance relay? Remember, the low impedance relay is a very smart relay. You look at it, it monitors. What does it monitor? It monitors the status of the disconnector. It monitors the status of the circuit breaker. And it is so smart, it can say, hey guys, my circuit breaker is open. If there's a fault here, it cannot be a busbar fault. So why do you want to trip the busbar? Don't trip the busbar. Send a signal and trip the other side. That is called an end fault. Because it's smart enough. End fault. But it's only applicable if you have both are low impedance. If you one of them is high impedance, then it doesn't work because the other one is filtered wrongly. So it's called an end fault. But from what I know, I don't know whether anybody, Federic or any of the ETD guys can confirm. But nobody used, as far as I know, that this concept is not used. And the same thing applies. Okay, this is essentially the same thing now, talking about end fault and all that. But the same thing also applies. Okay, I think maybe I didn't have a drawing. Okay. What happens if you have a fault here? You have a fault here, remember this overlapping? You remember this? You can see here, this, remember again, Kennedy, your question about the CTs, you can see here, core 2, core 1, core 3. Okay, yes. There are all these different CTs. So what happens, the bus section, what happens to the fault here? The fault here is again seen by both the main, this side and that side. So what they then do is, in the case of a low impedance, this can say, if the bus section is open, if a fault occurs here, it has nothing to do with the other side. So it will trip and this relay, this CT is a fault. You say, this one belongs to the other side, but never mind. I will use this one to trip this side. So you can do that with this low impedance. But whether anybody wants to use it, as I told you, from what my understanding is, nobody using it in Malaysia. But as I say, only if you have this, what we call, both are low impedance. So this is my understanding of what the application in Malaysia for busbar protection. So not in the good old days, you notice I always talk about good old days. So you can, in the good old days, we only got high impedance. So high impedance relays, and we have a single set of relays, and this was previously used up to 132 kV. So we no longer use this. And then we have high impedance with duplicate or parallel identical relays. So this one is good used in Sarawak. I won't go into detail because it's a bit more complicated. But what will happen nowadays? So in the TMB system for 132 kV, they want a low impedance. As far as I know, they don't accept high impedance anymore. If it's a single scheme, then we have so just now whatever I talk about, remember the N fault, the fault in the bus section. If you have a 132 kV, we can use it. So 132 kV, only one low impedance, you use it. What happened to 275 kV? 275 500. So there are two choices at this moment in TNB. They allow you to use a low impedance plus a high impedance or two low impedances. Up to you. Okay, so far, of course, the project that I've seen, people will use only this option because this is too expensive. Okay. Then this is the last drawing. Oh, I'm a bit ahead of time. Okay, this is the last drawing. So this drawing shows you the how the CTs are shared. So you can see in this case, as I went through beyond just now. So we have, say in this case, maybe 132 or 275 kV incomer. So you can see this is our incomer because I got main 1, main 2. Then I got bus bar 1, bus bar 2, and these are for the high impedance. One is for the this is for the discriminating zone, this is for the check zone, and in between we got two other CTs. One used for power meters and the other one used for low impedance. So you see the low impedance, one thing is they don't go and separate, oh, I need a separate one for main, I need a separate one for check. They don't do that. They only have one what we call low impedance relay. And you can see again the same thing on this side. So you can see bus bar protection, reserve, bus protection, main. So these are the two maybe high impedance. And then you got the low impedance here. You can see one low impedance here, one low impedance here. The advantage of using low impedance is you can share the CT with other applications. You can see here, breaker failure, backup, with low impedance. You can share. Whereas with a high impedance, you're not allowed to share. That is the rule. So that are the arrangements for typical bus bar protections. Oh, I finished a little bit ahead of time. So this is the last slide. So this is just a repeat of what I told you earlier. Remember the edge arrangement. So what I want to show you here is for this edge arrangement, remember I told you the 1, 2, 3, 4. So this is the overall check zone. It covers everything. I tried to show you the main 1, main 2, or the result very difficult with this drawing, so I can't do it. So I just put here, hey, this is the discriminating main 1, this discriminating main 2, this is the discriminating reserve, and the check covers everything. And then there are two overlapping zones, both at the bus ties. So there's one overlapping zone here, there's one overlapping zone here. And that brings us to the end of 1, 2, 3, 4. One check zone, two overlapping zones. Of course, you got to remember which is which. 3 discriminating zones and 4 relays. Okay. So, any questions? Otherwise,
yeah, 87B.
Sorry, who is that, please?
Albert here. What is that 87B?
The additional what?
87B.
The D, yeah.
No, the title then 87B protection.
Oh, the title.
87B. What is that?
Oh, okay. Albert is I must tell you is a more instrument guy. He's attending just to learn something. Okay, what happened is 87 is an American number called NC number, is used to what we call denote certain relays. So for example, an overcurrent relay is called 51, fault relay is called 51N, distance relay is called 21, and 87 is a differential relay. So we have different type of differential relays. We have different relay for generator, we have different relay for lines. I'll show you some of them now. Okay. Because by the time you reach here, I thought that you'll be very familiar with these numbers. For example, you can see here F94. Okay. Here doesn't say more. So all these are NC numbers, but I'll show you a few that appears here. 52 is a circuit breaker, okay. One I show you actually is here. You can see this. Yeah, it doesn't appear. It appears somewhere else. It appears later, early on. There's an 87B and there's an 87L. If you want, I got to go back right at the beginning. Okay, maybe I'll just go back since you asked. Okay, Albert, and we still got time. So, okay, this here. These are numbers very common in if you are familiar with relays, which as I said, but I assume that you're quite familiar. You can see this 87L. So 87L means it's a line protection, differential protection for the line. 87B, differential protection for the bus bar. So you can see the line, the protection, the bus bar, is protecting all this. This 87B. 87L is looking into the line, okay, and then 87T of course is transformer, 87G is a generator, and so on lah. So those are the typical numbers that are used in American system, and a lot are used also in even European manufacturers lah, because it's a very convenient way of. So 87B, I tripped. Where's the fault? So, okay, since I can amend it to in the revised note lah. No problem. Okay, thanks for the question. Yeah, sorry, the question.
Yeah, on here, I have a question. Because you said the TMP uses now they implement low impedance. This is only for their own substation, right? The customer, they're still allowed high impedance.
Well, customers, we all very good customers. We all follow what TMP is doing. No?
Oh.
I mean, you. Okay,
okay.
What Ong is asking is, for example, this question. Okay, I assume, let's say I put this 132 kV substation. Okay, according to the way I read it, is that a 132 TND wants a low impedance. I want to save money. This 100,000, maybe 10,000. So can I use a high impedance? You can try, but I won't be surprised TND insists that you use a low impedance. I assume all along that everybody been the good boys. Okay lah, for the TND one we give lah. Don't ask for trouble lah. But you can try. Maybe they might say, okay, yeah, I can. So why you ask this question, Ong?
No, their question is, when did they implement this? Because 2018 they still allow.
Is it?
Yeah, because the MRT project they use high impedance.
Okay, maybe I'm wrong, but that's my understanding. Okay, Frederick is too new to this, so I don't know whether Frederick can answer. But all the drawings that I look at, okay, sorry, I didn't look at 132 kV drawings because nowadays, 132 kV like nobody very interested. So all the projects I've looked lately are all 275 kV. So they all got a picture of high and low. You may be right. Maybe this is an assumption made by me. Maybe I'm not quite correct. Maybe I don't know. Yeah, maybe you can try. No harm.
Okay, no, I'm just asking on it. Okay.
Yeah, maybe.
Okay.
Okay. Any other questions? No other question.
This one online. By Mr. Hyang.
Hyang. Oh yeah. Okay. So sorry, Hyang, you asked a question and I didn't answer it. Okay, anyway, you got a second question. Sorry.
What is?
Oh, you know why I didn't answer it? Never mind. Okay, you asked the second question first. Anyway. Okay.
Okay. What is the typical 87B operation current setting value for zone 1 and check zone?
Okay. Hyang asked a question. What is the typical setting for 87B, the bus bar protection? I have not done bus. Okay, maybe I ask Ong. Ong is more familiar with it than I am. But Ong, would you be able to remember what was the last time you did 87B? What was the setting?
You're talking about low impedance, right?
It doesn't matter high or low, it doesn't matter.
Low impedance, I think, is above 150%.
150%? Wait. We're talking about bus bar protection, 150% or what?
Because I think low impedance, they allow for if you want city failure, you don't trip, something like that. I cannot quite.
They allow what?
If you have one city failure, then you don't trip. So they allow the. That means unless it's a fault, then you trip.
I lost.
That if it's a full load, let's say it's a full load, right? So they allow let's say just a loading, and then one of the city fail. So it will not trip because of that. So they set it on the higher side.
Is that so? That's news. Okay, well, maybe let's change the question first. Let's look at high impedance first.
High impedance, I think, is 20%. I think. So.
Okay. My guess is, if you ask me, I would set around 30%. That's my guess, lah. Okay. Why? Okay. And the other strange thing we must look at it. You can see this is a high impedance, and the high impedance, the ratio, CD ratio is very big, 4,000. The low impedance, the CD ratio is much smaller, 600. Let's say 10% of it, lah. Very easy, lah. So you can see the low impedance has got 600. 600 amps. Let's go and put, as I said, Ong said you put at 20%. 20% of this is what? 800 amps. If I put 30%, it's 1,200 amps. Now, okay, so my guess is between 20 to 30%. Why do I put 20 to 30%? The answer is very simple. Because the fault current is so big. Because if you have a bus bar, the CD is 4,000 amps. What do you think is the bus bar fault current? Of course, what happens that if you go and buy a 275 kV switchgear, the rated short circuit current is supposed to be 40 kA. That's TNB's requirement, 40 kA. And I think 132 is 31.5. So let's assume that the fault current is only 20 kA. And 20 kA, the fault current is so high, let's say 50% of 20 kA is 20,000 amps, 10 or 40 kA. But let's even tell 25%, 10,000 amps. I got 4,000 amps. What do? I set at 1,000 amps. 10 times more. So plenty of fault current. So I can afford to set it much higher. So so that is what I would do. So Ong is probably right. Somewhere between 20, I maybe will go for 30. Okay. So around there, 20 to 30. That's high impedance. But the low impedance is something new to me. Ong, you said how many amps again?
It's because it's a bit speculative. That one. I mean, you can set the same like the high impedance, but also you sometimes they allow. Let's say you have one city fail, right? Then you don't want to trip the bus bar, so they set higher than that, so they ensure that it's fault, not a city failure.
Okay, what Ong is saying is, okay, number one, you said how many amps again? How many percent?
We're about more than 100%.
Okay, so he's saying that you're going to set at say let's say 100. I think you use 150 lah. If you say 150, it will be 900 amps. Then remember, I'm setting my high impedance at 20 to 30%, which is also around that figure, 800 amps to 1,002. So effectively, his 150% would be very close to the 20%, 30%. And what Ong is saying is that, hey, what happens if you got a CT open circuit, CT failure, or actually more open circuit? So what will happen? The low impedance has is very smart, so they probably can detect it, and somehow what's the maximum load you can carry? Maximum load you can carry probably is less than 600 amps. Okay, so you can see the main one, main two, only 600. Very strange. This main two is 1,002. So I don't know why. This I didn't notice it. This 600 is 1,002, and even you said at 1,000 amps, is probably above the load. So what you're saying, I don't want to trip during load, but it's something new to me, which I didn't think, I'm not aware of. So Ong may be right. So the answer to your question, Hyang, are we talking about the low impedance or the high impedance? So the high impedance, if you look at it carefully, I would set it in terms of amps. I would set it maybe about 1,000 amps like that, somewhere in that region. Okay. Have I answered your question here? Now, Hyang also asked a question about the distance relay, the timing. What's the question again about the distance relay timing?
The question was, why is distance zone 1?
Yeah.
Why does it need 150 milliseconds?
Okay. The way Hyang asked the question, Hyang is actually a tester. So now he's obviously very familiar with what we call distance relays. He's very familiar with the timings and so on. Now I'm trying to get ready for the next part, which I forgot lah. Now if you have a distance relay, and you're obviously talking about backup lah, because as I said, distance no longer used as the main, as a backup. So why is it set at is it 150 or is it 300? I can't remember now. What's the figure again, Win?
150.
150. And the answer is very simple. The answer has something to do with maybe I jumped the gun a little bit lah. I show you the next slides for breaker failure. Since we've got a bit of time, I just jump the next slide. Now this is showing you what's called breaker failure relay. So breaker failure relay is like this. What happens? You send a signal to a breaker to trip, and the breaker didn't trip. So you want something called breaker failure to trip a bit slower than the normal protection. So you can see we have a fault here. So there is the main protection. The main protection trips here, and then the breaker will trip. Remember, the main protection plus the breaker. This whole thing will take about 100 milliseconds. Remember at the beginning, right at the beginning, I said the total fault time TNB allows is the main protection must clear the fault in 100 milliseconds. What happens if it doesn't clear the fault in 100 milliseconds? Something has gone wrong. Either the breaker has failed because the relay operated and the relay didn't, the breaker didn't trip, so breaker has failed, or the relay didn't even operate. So in other words, there was this fault. The main protection failed. So the other protection didn't know. So you say, hey, I'm waiting for the main protection to trip. Main protection didn't trip or breaker failed. I don't know which one. So what they then do, hey, after allowing for the 100 plus a margin, then I better go and trip. So that's why we trip at something more than 100. Okay, so that the 50 is a margin. And in this case, for the breaker failure, we'll talk about it later. I think they also set it about 150 milliseconds. So Hyang, if you can look at your record, you come back next week, you tell me what is your breaker failure time is for the same substation. But what I noticed now is that 150 has now been changed to as high as 400 milliseconds, 450 milliseconds. That's the latest I have. So if you want Hyang, what you can do is, you can email to me or you can email to the WhatsApp group. Look at, I assume that you are going to have a breaker failure. I assume that you have a what we call the bus separation scheme, and you have a zone 2 protection. Tell me the timings of these three. Okay, in other words, if you want, I can send put in the WhatsApp group. Breaker failure timing, there are two timings because there's a retrip and a second trip. The zone stage 1, stage 2. Then we have the bus section, and then we have the zone 2. So I'll put it in the WhatsApp group. You tell me, and then we'll look at that figure later on. Okay. So hopefully that answers your question. Any other questions, Win? Any other question from the group?
No, not. I don't see any question.
Yeah. Okay. Anyway, okay. I think I forgot to get ready this one. Okay. I need to do something before I'm ready for my test. Okay, I go to reset the results. clear. Wait, clear all results. Okay. Okay. So no more questions.
Mr. Lee.
Yep. Go on.
Yeah, I'm Chu here.
Okay. While Stu is getting ready, asking this question, what I want you to do, everybody, if possible, to go and join this AHA slides, and what you need to do is you need to just log on. How come? This is the wrong question. Sorry, Chiu. I must have got the wrong question. Oh, sorry, I went to. Oh, it changed. Give me a minute. I got to go for trans. Here. Okay, so. Oh, no wonder that's why there was this. Okay, just to make sure, I'm going to clear the results. Just to make sure. Okay, clear student results. Clear. Okay, clear. Okay, let's go back to here. Yeah. Okay. Now, what I'm going to do is I'm going to do a test, a quiz. Now, this quiz is for fun. Okay. So all you have to do is you log in using your device, your handphone, your computer, whatever. Okay. And you log into this. Okay. You have to give yourself an ID and a character or what they got avatar, I think. Okay. And then you wait for the test to begin. It's about, I think only 8 questions, so it's a very simple test. It's just for fun. It will give me a feedback of how well you understood what I'm trying to tell you. So of course, if you do very badly, then I say, yeah, this trainer not very good lah. So hopefully you all do well. So my intention is to get everybody to pass, and I'm going to help you by doing a last minute revision before you sit for the test. Okay, so hopefully you all do join. So please log in to this site. Okay, can all of you do it? I can accommodate 200 people, so we should take everybody. Okay. Okay. So you log in, and before we start, I'm going to show you some of this, like what we call last minute revision. So please join in. Okay. Okay, please join. Okay. Okay. Now, Chiu, please ask your question now. Sorry about the interruption.
Yeah, no problem. Back to that, the low and high.
By the way,
yeah.
SK.
SK.
Oh.
Yes.
Hey. Oh, yes.
No see.
Renhil.
Yeah.
I haven't talked to you for a long time already.
Yeah.
You're keeping a low profile. Okay, SK. Yeah. What's up?
No, back to that, the low and high impedance issue.
Mm-hmm.
So is it related to the system earning?
No. Low and high impedance is just a matter of preference, that's all. It has nothing to do with how you earn the system.
So how?
In other words, now let's go back to an example. Let's go back to restricted fault relay. Of course, obviously you miss all that, SK. Now let's go back to a restricted fault relay. We have 2 choices for a restricted fault relay: a low impedance and a high impedance. Bias differential relay, we have to go for bias is basically a low impedance. And the same thing with busbar protection, we have a low and high impedance or low impedance. It has nothing to do with whether it is high or whether it's the earth through the NER or through the directly earth. In the case of transmission, what do we have? Solidly earth. But in the case of 11 kV, 33 kV, it's earth through a resistor. And both of them are acceptable. Both, as you saw, the 275 kV, the busbar protection, you can have a high impedance, low impedance. And at the what we call the 11 kV, 33 kV, you also have a choice. It's a matter of which one you prefer, that's all. So to answer your question, no, there's nothing to do with low or high impedance. I mean, the whether
Sorry.
it's NER or solidly earth, nothing. It's a matter. It's a matter of which method you prefer. That's all. Both have the same sensitivity. Both can have the same operate in the same way.
But how they? Therefore, my understanding, this of low and high impedance, those are related to the system earthing. I mean,
No. Yeah, that anybody who told you that give you wrong information. It's nothing. Because okay, let me put another way. You just saw the 275 kV bus bar protection. Did you see a high and low impedance?
Yeah.
Yeah. I have a project now, for example, it's a 275 33 kV transformer. What do? 275 kV side, we have not restricted fault lah. 275 kV, we have low impedance. 3311, we also have, no, this is high impedance, but you can have low impedance. Sorry, I was wrong. Everything was a high impedance in this case, but you can have low impedance. There's no restriction because they only look at how do we set this off. So why was I wanting a low impedance, high impedance? So certain advantages, certain disadvantages. Okay, but if you want to talk about that, then that's a different question. So we'll go back to I did a session on differential relays where I talk about the three types of differential relays. The bias differential, the low impedance, and the high impedance. Unless you have to go back to those topics which are done much earlier, I think sometime last year.
Oh, that one I missed that one.
Yeah, a lot of you missed. Well, one of these days we may repeat lah. Okay. How come I don't see anybody logging in? Can anybody? Has anybody logging? Agong, did you log in?
To key names or anything?
Yeah, you need to key in to log in this, and then you key in your name and choose a symbol.
When I key in the website, the link, I can't key in any name.
Hey, funny Okay. What happened? To join? Okay. Because I've been doing this unless something happened to my. Okay, because okay, I'm at our slides. I'm at this. Okay, I log in again. So yeah, normally you try to join, right? Win. Am I right?
I just key in the.
Yeah, normally when you're log in, I can see who has. Because the only thing I did was, it seemed to be like looking because I normally don't see this all this. Oh, I have no idea what happened. Oh, I must come here.
Okay, now we can.
Sorry. Because what happened? I added the two slides, and after lately, and I've never done the test after that. Sorry, and I didn't realize I got to come here before. Okay. Then maybe I don't know whether I can go back or not. Now. Okay, thank you. So I hope everybody join. Hopefully, I can go back to the previous slide. Those are like the division. Very good. I can see a very good response. Win, how many people have we got at the end now?
We have 99.
99, yeah? Out of, let's say 100 out of 30. 130. About 80% attendance. I was hoping for a bit more. Never mind. Okay, very good. So there should be a report that tells me how many people join in, but now I don't see that. Okay, yeah, see at the top here. 50, 51. Very good. Okay. The only problem now is, can I go backwards? I hope so lah. Because I want to do a last minute revision, give you tips so that you can pass the test. Okay, 56. So I hope for at least 70 lah. 57. It's a fun thing only. Don't worry. I obviously I do not know. Especially you use some names which are totally new to me. I wouldn't know who you are, and I'm not interested anyway lah. I'm more interested in seeing how you do lah, so that if I find that there are a few weaknesses or then we'll try to see what we can do lah. From previous I've done a few sessions. I found that the weakness was some of the points that I've gone through somehow was not clearly understood. I don't know why, but then we're happy to pass. I'll do a last minute revision, at least some of the topics. Our slide. Okay. Oh, it's almost 1 hour. Okay, wait another 3 minutes. 53. Please, 63. Oh, I can't close this now. I have a problem. I cannot close it. Why? What is I'm supposed to do? Just enter your message. I don't know what am I supposed to do with this. Can't get rid of it. Okay, I will start the test. Let me try to go backwards. Hope I can. Okay. Okay, so these are the two slides that I went through with you. Okay, so remember I told you this is an age arrangement. So I'll be talking about the age arrangement many times. So age arrangement means that you have two lines coming in with a bus section and two circuits going to the cable to the transformer. Okay, and okay, this drawing is there's some mistakes here, and you can see that if you have parallel transformers, then you need to close in everything. Okay, both breaker A here, breaker B must close, and the current will flow through here, and then this creates a problem. Later on, if one of the relays fail or one of the protection relay fail, where is the backup? The backup actually is here. So if there's a problem tripping during a fault here, if there's a fault here, the main protection will trip within 100 milliseconds. So if there's a problem tripping during 100 milliseconds, where's the backup? These relays don't provide backup. The backups actually are here. Why? Because the only relay is the distance. The current differential cannot back up. The distance is looking the wrong way, the other way. So this is the backup here. And this backup, if they both trip, they both trip together, which is no good. You've lost both feeder. So you must somehow initiate a tripping that somehow open this breaker before these two can trip. But that's actually later. Okay. So the second slide I want to show you is for the bus bar protection. So this is the bus bar protection for for the what we call double bus bar. So you got I remember the 1, 2, 3, 4. So it's got I forgot to do the test. It's got 1 check zone, 2 overlapping zone, 3 discriminating zones, and 4 relays. So that's what it means. So okay, now let's hope. Okay, we are ready to do the test. Okay, about 60 people still. Okay, let's do the test. So how you do the test is like this. Okay, I'm going to start the game. Hey, how come I made the question? Sorry, I must have missed. I went and clicked. Okay. Okay. Let's start the test. Okay. So you're given time. Okay. A certain limit. So the current differential can be used as the main protection for the following. And whenever you see a yellow, means that I need 2 answers. So we have 4 answers here. So you're supposed to take 2 answers, because that's what I told you. So can you please pick 4 answers? 2 answers out of the 4. Okay. So we got 5 answers, sorry. So which are the 2 answers? The current differential relay is used for, and you only have about 15 seconds left to answer. 10 seconds left. Bus bars, cables, lines, generators.
Where to put in the answer?
The last one is also a bus bar. So sorry. Okay. Time's up. So if you say bus bar is wrong, I'm sorry. So the answer I wanted was cable and lines. So everybody got lines, some got cables. So okay, so the last one obviously that I made a mistake somewhere there. Okay, so well done. Okay, then question 2. In this case, only one answer. The communication link for a current differential relay consists of. So what's the communication link for a current differential relay? Is it a copper wire? Is it optical fiber? Is it a radio link? Is it a microwave link? Is it a pilot wire? So one answer. So 10 seconds left. Okay, 5 seconds left. 3, 2, 1. Hope everybody get correct. Very good. Everybody got correct. Wow, fantastic. Okay. And this is called the leaderboard. So in this case, a lot of people were correct. So Cairo, VKR, okay, Tam, okay, Tantuwi probably, TKB, I don't know, Wei Song, okay, so good. So a lot of you get 100% lah. Okay, very good. So question 3, there are only 8 questions lah. So when the communication link fails, the current differential relay, well, I want 2 answers. What are 2 answers? It will always trip during internal fault. It will be unstable during external fault. It will not operate during internal fault. It can be programmed to activate zone 1 of the distance relay. So 2 answers. You got 15 seconds left to answer. 2 answers. Okay, 3, 2, 1. Hands up. A lot of people correct. Yes. So, in fact, nobody got. A few got it wrong. It will always trip during any internal fault. No, it will not trip. It will not operate anymore. So, most of you got correct. Very good. Question 4. Which of the following statement is true? I only want one answer. A current differential relay can operate as a backup. A current differential relay can operate both as a main and backup. A current differential relay can operate without its communication link. A distance relay cannot operate without its communication link. A current differential relay can only operate as a main. So in this case, I only want one answer. So which is the answer? 5 seconds left. I think everybody get correct. Hey, how come a current differential can operate as a main? No, remember, as a main and backup. Remember, a differential relay only operate as an internal fault. Only operate as for internal fault. It can never operate as a backup. Okay, it cannot operate for external fault. And the distance relay can operate without a link. Because distance relay, in fact, remember the first drawing I showed you for the transmission line? There was no communication link. TMB doesn't use it anymore. So the only answer I wanted was a current differential relay can operate only as a main. That was the answer. It's a very simple answer, but maybe you're overthinking. So let's look at leaderboard. Wow. We got lost. Okay, Cairo is still in the lead. Tantuwi, CKB, I don't know who that is. LY, not very sure. KH. Obviously, there are others who are also doing well. So you can go further down. After Chua, Tam Wei Shan, then start to less than 100% already. So okay, never mind. Let's move on. So question 5, we are halfway through. Okay, so I want two answers again. Which of the two statements are true of a distance relay? It is a non-directional. It has a minimum of 3 zones. The relay characteristic is shown on the VI or PQ plane. The relay setting are in volts and amps. Zone 1 is set to overreach, and zone 1 and zone 2 normally have a circular mode or quad characteristic. I want two answers. Okay, you got 10 seconds left. Time's up. Okay, so yes, most of you got correct. Okay, first one nobody got correct, nobody did it. Second one, the relay characteristic is shown on the VI plane. No, it's shown on an RX plane. Remember, you got the resistive and the reactive component. You got impedance. So what is impedance? Resistance and reactance. So it's shown on an RX plane. And the relay settings are in volts and amps. The relay is an impedance relay. So the setting. Remember the question, what are the settings? The characteristic, the impedance, and the angle. So that's why you lost marks. And the third one, zone 1 is set to overreach. No, zone 1 is set to underreach. It's set to less than 100%, underreach. Zone 2 is overreach, more than 100%. So you have lost some marks on those 3. Okay, question 6. Okay, now we come to this discriminating zone. That was the one I just did the revision for you. So how many discriminating zones are there for the high impedance password protection? 150 plus. Discriminating, only on discriminating. Remember the figures 1, 2, 3, 4. Discriminating, how many zones? So it's a very simple answer. 1, 2, 3, 4. So the choices given to you also 1, 2, 3, 4. Oh, no, 5 even. Sorry. Okay, you got 3 seconds left. And the answer is a lot of you got correct. In fact, everybody got correct. Fantastic. Wow, very good, very good. No, the few, sorry, the few got 4. 4 is the number of the total number of zones, and a few got 2 even. Sorry. So, but the good thing is a lot of you got it correct. Remember the 1, 2, 3, 4. The 3 refers to the number of discriminating zones. The 4, including the check zone, is 4. Discriminating plus check is 4. Okay. See a lot of people with 100%. Oh no! Oh, nobody got 100% already. How come? How come? Fort Boy. Who is Fort Boy? Okay. Lee Ming Yuan. Oh, Kelvin, Aaron. Okay. Let's. I'll show you the final score later on. Okay. Last 2 questions. Again, password protection. Which 2 of the following statements are true of? Which 2 of the following statements are true of the high impedance password protection relay for TMB? Okay. Total. This is more or less a repeat. Total of 3 check zones. Total of 3 overlapping zones. 2 out of 3 tripping scheme, and failure of a check zone will disable the entire passbar protection. So I want 2 answers. And the last one is related to the question asked by Pang just now. So 2 answers. This is slightly tougher. Okay. Oh, a lot of you got it correct. Okay. So the answers I wanted for the last 2 is a 2 out of 2 tripping arrangement. Remember, password protection must have a logic and condition. 2 out of 2. And if 2 out of 2, if one of them fail, then cannot trip. So the failure of the check zone means no tripping. Okay. So if you say the total of 3 check zones, remember I told you 1, 2, 3, 4. So the check zone is only 1. and total of 3 overlapping zones. 2 refers to overlapping zone. So that's what it means. And then the last question. I got other questions, but those are meant for the second session now. Which two of the following are well protected? Well protected means 100% protected by the zone 1 or zone 2 of the backup protection of this transmission line. Okay, which two are well protected? 100%. Is either within zone 1 or zone 2. So external line fault, downstream bus bar fault. Oh, not much time left already. 2 answers, huh? Ah, very good. A lot of you were correct. So, okay, where you went wrong? External fault. External fault, it doesn't prove very well because it only covers 20% on the next line. Up bus bar fault at the back, it's not well protected. Okay. Okay, and then the downstream transmission transformer fault also not well protected. It doesn't protect 100%. Okay, so we are at the end. Okay. So this is the final result. So, okay, the top scorer, we got 8 questions, so the total is 32. So, TKB, KH, the 2 top scorers, X, 24, Woman has been appearing constantly, I think, previously. 24, Tam Wei Shan, also 24. Okay, Lee Ming Yuan, also 24, very good. Sorry. Sorry, I went in. Okay, wait, I pressed the wrong button. Yeah. If you want, anybody want to see the score, then I got to go back. See whether they can find it or not. Sorry. Okay, let me see if they can find it. It should be this one. Loading results. So, okay, where is the... There's a way to go further down one. Yeah. Here. Okay. So, then after that, after Tam Wei Shan, Lee Ming Yuan, HH, 24, 4Boy, 24, all doing quite well. Kelvin, 24, Aaron, 24. So 24, a lot of people. Fred, Fred, you got 22. Chua, 22. LY, 22. Cairo, you were the front runner. What happened? MSL. Okay, now we got to start with. But still a lot quite high. 20. Tan Tu Vi, KSR, not sure who. VKR, don't know whether it's Venkat or not. Arman, okay, 20. Okay. KZ must be Kamaruzaman. Fauzi, Wei Song. So 16. Then Lost. Okay, KW, not sure who. SH, not sure. Wilson, 16. Okay, I'll just flash down so you can see your score. EJ, EHJ must be Tang, I think. HA, not sure who that. Ong, 16. Win Xiao, 16. Press enter. Okay. So not everybody answered. Only 20 of you answered. Hey, how come no more? Wait, there should be some more. Okay, I won't show the rest. If anybody interested, I'll share with you. Okay, so that's the end of the session. I've taken about 15 minutes overtime, which I'm a bit surprised. I thought I would require another half an hour. Okay, so we are finished. So, any more questions? SK, Chiu, if you want to discuss further about your high impedance, low impedance, we can continue. If not, officially we are finished. Any last questions before we call it a day? Anybody? Hyang, you had any more questions? Visa? Your Brunei experience will be different from what we have here.
Ali, one question.
Shamsul, right?
Yes, Samsul. During symmetrical fault versus asymmetrical fault, the calculated Z still the same, right? For the 21?
You're asking a different question altogether. Your question about symmetrical and asymmetrical fault.
Yes, I just want to confirm the calculated Z, is it still the same during symmetrical fault versus asymmetrical fault?
Okay, I tell you what, if nobody got any more questions, officially we'll call it. So thank you very much. I will try to answer. If anybody, of course, want to listen to what the discussions on this question by Shamsul, welcome. Otherwise, I will see you next Tuesday. And if Hyang, if you want to share whatever relay settings you have on the group, in the group also, please do so that we can have some discussions. Okay, the question asked by Shamsul is about symmetrical and asymmetrical. Now, first of all, we got to look at what do you mean by symmetrical and asymmetrical. Symmetrical, if you ask me, my interpretation is that it's a three-phase balance fault without a DC component. Okay, but it's a fault without a DC component. Is that what you meant, or is that something else
Yes,
that you have in mind?
Correct, Ali. One is without DC, another one is with DC.
So in other words, what happens if you have a fault current? What you would expect to see, I want to see a nice sinusoidal wave. The plus and the minus are equal, and that's what we learn in college, in uni. Okay, that's what we learn. But in real life, it's not like that. In real life, when you have a fault, the fault current has what's called an offset. If anybody wants, don't know what I mean, I can show you a slide. Offset meaning that there's either the positive or the negative is much more. Then in other words, the two of them are not equal. The positive can be very much higher. So we call it asymmetrical. So what do you want to know about asymmetrical fault current? What's the difference? The difference in between them is to know the fault current, we got to know what is the Z. That's all. All right. You know what I mean, right? You use the V divided by Z, and somehow you use that to calculate the fault current. But if you want to know about the asymmetrical part or the peak value, then you have to go into what's called the X upon R ratio. So I will show you something. It's not the best one, but it will be enough for the time being. So okay, somewhere around here. I'm going to wait for the slide to get there. Oh, okay, I'm almost there. Oh, sorry, no, it's the one before that. Wait. There's one that says, okay lah. This one. So this is called an asymmetrical fault current. Oh, you can't see very well, but I'll show you another one. This is called, again the same thing. What happens? The AC, the positive negative cycle is much more than a negative cycle. Okay, I didn't show you very well, but both of them didn't show. I didn't realize it. I thought it showed. So calculate this current. Okay, let's calculate the symmetrical fault current. To calculate symmetrical fault current in per unit term, you need V divided by Z. That's all. But to calculate the peak value, this is called the peak value. We need an X upon R ratio. The higher the XR ratio, the higher will be this value. And the typical value will be, if we assume the X upon R is about 14, then technically speaking, the peak value of this will be 2.5 times the RMS value. So the answer to your question is no, they are based. They need different data to begin with. The symmetrical only needs the V and the Z. The asymmetrical needs the V and the Z and the X upon R. Does that answer your question, Shamsul?
So during the asymmetrical fault, so maybe example for transformer, we set 70% of the transformer impedance. So
70%.
For the generation, we set about 70% of the transformer impedance for zone 1. So
wait, sorry, I lost you. You are trying to find the fault current, right? Okay, so you have a generator. Yeah, where's your fault? At the generator terminals or after the step-up transformer?
For the 21 G, we set based on transformer Z. So we set based on Z.
That means you're looking at the fault after at the transformer HV terminals, lah.
Yes. So
okay. So why is it at 70%? Oh, I see.
Okay. Internal zone, for internal zone of the transformer.
Okay. So what you're saying is that you calculate the fault current and you put a multiplying factor to make sure it overreaches the transformer, overreach beyond the transformer.
For the zone 1 underreach for the transformer, we set only based on 70% of transformer.
Okay, I didn't understand the 70%, but the way I guess is, okay, when you have a generator, obviously this is outside, nothing to do with what you're talking about now, lah. When we have a generator, what we call 21Z, the 21Z, how do you want to set it? You must come up with your principle. Do you want to set it at to protect the generator? Do you want to protect it to protect the transformer? Do you want to go beyond the transformer? So, that's the first question you must ask.
Usually, for the protection setting for 21 generation, we set it for zone 1 is underreach for the transformer. But
so you set it to less than the transformer, to less than the transformer fault current, maximum fault current.
Yes.
Okay.
At the same time, we still can detect the fault in the generator since we locate the CT at the neutral, so we can detect fault in the generator and also at the transformer.
So what your relay must do is it must cover 100% of the generator and maybe let's say 50% or 70% of the transformer, lah.
Yes, correct.
Right, but you cannot calculate that way. The only way you can calculate it, you can calculate the fault current at the generator terminal, you can calculate the fault current at the transformer terminal, and then you can say I want to protect less than the fault at the transformer terminal. You set a lower current than that, lah.
We calculate the VT for the VT located at generator terminal. So 70% is actually from the VT, from the VT until the transformer.
No, okay. What happened is, if to be honest, I've never done generator impedance, lah. Now what happened is, if you have a fault in the generator,
yes,
the possibility is the fault current coming from the system. Okay, the generator has own fault current, but there's a current coming from the system, and that one will then give you a certain voltage. Then, if you have a fault outside the generator, let's say at the transformer terminal, then you got a fault current coming from the generator. So what you're saying, you don't want that generator 21Z to operate for a fault in that condition.
Actually, for our relay will detect fault at the generator, internal in generator, and also in transformer. But for the zone 1, only up to 70% for zone 1.
So the 70% is a bit of a, because the problem
70% is starting from the generator terminal. From generator terminal
to I will put it this way, lah. I will put it. Okay, I'll give you a very simple case, lah. Let's say the fault current at the generator terminal, let's say 10,000 amps. Let's say, lah. Your fault current at generator is 10,000 amps. Okay. So, and then the fault current at the transformer terminal, let's say, at the same place that you have is 5,000 amps. So when you want to operate at you see the problem is when you want to set the relay, how are you going to set it? Because if you really want, you got to calculate what is the. You really got to do this. If you ask me to guess, you got to model a generator with a voltage. Then the generator is only internal impedance. Then you got transformer impedance, right? So you are saying that hey, there is a fault at the transformer terminal. Let's say the case, don't talk about 70% first. Let's say we talk about the case that the transformer terminal has a fault. So can we calculate that impedance? You should be able to do it, right?
Yes.
That impedance actually is equal to the transformer impedance.
Yes, correct.
So what you're saying, we're going to set it at 70% of that.
Yes.
So what's the problem here?
I just want to confirm when there is asymmetrical fault at maybe after our setting, but I want just to confirm the calculated Z. Is it same calculation?
Okay, you're asking whether the asymmetry will affect the impedance.
Yes, the relay calculator.
If you ask me, my guess is the distance relay will have a filter that will remove any DC component.
Okay.
Forget about your generator. Let's take a line. If I have a line, there's a fault at the end of the line. In reality, there will be a asymmetrical fault current.
Okay,
right?
okay.
I'm talking about normal transmission line. Transmission line, we have a fault at the end of the line. Right?
Okay.
Do we go and look at it and say, hey, my DC component, how will it affect my distance relay setting? We never do that. Why we don't do that? Well, you can say that the distance relay has its own filter, and that filter will remove the DC component. So the DC component is 0. So what are you left? You're only left with the AC component.
Okay, now I understand. Okay, thank you, Ali.
So whether your metal component, I don't care, because it's removed by the DC, by the filter.
Okay. Now I clear. Thank you, Ali.
Okay, by the way, just in case, I don't know whether you're interested. Are you interested in SKM? Or are you interested in power system studies?
I'm interested, but for the time being, I didn't have a chance to learn it.
Okay, I don't know whether you can or not, but what happened is, I'm sure you know Shahiwan, right?
Yes, Shahiwan, yes.
Shahiwan is proposing to do a course on SKM for fresh engineers. So if you want, you can talk to him and smuggle yourself in. I'll leave it to you.
Okay. I will discuss with Shahiwan.
It's planning only. No, nothing is firm yet. No dates, no PO, nothing. It's just planning. So you can keep in touch with him when you see him. Okay. Because you're so interested in learning, I'm sure. But it may be a 5 days event, so maybe it might take whether you can spare 5 days or whatever. I'll leave it to you. Okay. Anybody else got any questions? If not, then okay. Thank you very much. So I'll see you all next Saturday, 9 o'clock or 8:30.
Question.
You got a question? Sorry.
Vincel here.
Hey, Vin.
The low impedance relay uses the 5P20 CTs.
You're free to do use any CTs that you like, but in general, yes. You will use a 5P, yes. There's no restriction.
Not like normal current differential, they need 5px.
No, high impedance must use 5px. No, sorry, high impedance must use 5px. Sorry.
Okay.
But low impedance, you're allowed free to do anything you like.
Okay. Thanks.
Because actually a PX, if you want, can be converted into a 5P. If you know how to do it, there are formulas available in the manuals.
Yeah.
Okay.
Okay. Thanks. Yeah.
Anybody else? If not, then I'll see you on next Saturday. Okay. Thank you.
Okay. Thank you.
So Win, send out the link for the video.
Okay.
You recorded the last part or didn't record this? The one.
Sorry, which one?
Oh, the last part about the asymmetrical, all that.
Oh yeah, it's inside.
You recorded, actually not necessary lah. Okay, never mind lah. Since you recorded, leave it lah. Okay. Thank you, Win. Good job.
Thank you.
Okay, bye.